Somewhere in the abyss of deep space, beyond the reach of ordinary starlight, exists an object that defies categorization. It's not small enough to be born from the collapse of a star, yet not large enough to sit at the heart of a galaxy like a cosmic monarch. It doesn't roar across radio waves or shout its presence with visible light, but in X-rays it screams. Its name is HLX-1, and it might just be one of the most important black holes ever discovered. Not because it's the biggest. Not because it's the closest. But because it may be something the universe has kept secret for billions of years, a missing link. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Black holes come in two familiar sizes. On one end, stellar mass black holes, roughly 5 to a few dozen times the mass of our Sun, formed from dying stars. On the opposite end, supermassive black holes tip the scales at millions or even billions of solar masses and sit at the center of most galaxies. These two categories have been studied, catalogued, and modeled for decades. But between them lies a yawning chasm in our understanding. That chasm is occupied by a theoretical beast, the intermediate mass black hole. Intermediate mass black holes, IMHs, are the Goldilocks of the black hole world, not too small, not too big. They're predicted to range between a few hundred to a few 100,000 times the mass of the Sun. And for decades, they've been the stuff of astrophysical ghost stories. We have strong models suggesting they should exist. We have theories that need them to make sense of how supermassive black holes grow. But for the longest time, we simply couldn't find them. They were too faint, too rare, or perhaps too shy to reveal themselves in ways we could detect. That made HLX-1 a revelation. When it was discovered in 2009, it wasn't just another bright speck in the sky. It was something altogether different. Located not in our own Milky Way, but in a galaxy far beyond, ESO 243-49, HLX-1 blazed in X-rays with a luminosity so intense, it couldn't possibly be explained by a small black hole. Yet it was far too faint to be a quasar powered by a supermassive one. It fit nowhere in the traditional black hole family. And that made it extraordinary. The search for IMHs has long been like searching for a mythical creature, like hearing rustling in the woods and wondering if it's the wind or a whisper of something legendary. HLX-1, however, didn't just rustle the leaves. It howled. Why does this matter? Because if HLX-1 really is an intermediate mass black hole, it could answer some of the most important questions in astrophysics. How do black holes grow? Did the giants at the centers of galaxies start small and merge over time? Or did they form rapidly in the early universe from massive clouds of collapsing gas? HLX-1 might be the missing piece that links the known and the unknown. In this journey, we're going to explore everything we know, and everything we still don't, about this bizarre and brilliant object. We'll talk about what HLX-1 is, how it behaves, how it was discovered, and why it just might be the key to unlocking the evolution of black holes across cosmic history. At first glance, HLX-1 might seem like just another celestial acronym, another catalog entry in the endless star maps of the universe. But buried in that name, Hyperluminous X-ray Source 1, is a story of cosmic extremes. It's not just a source of X-rays, it's one of the brightest of its kind ever detected, and it resides not within the Milky Way, but far beyond it, almost 300 million light-years away, in a galaxy called ESO 243-49. To understand what HLX-1 is, you have to understand what it's not. It's not a supermassive black hole. It's not a stellar mass black hole. It doesn't behave like a pulsar, or a quasar, or a neutron star. HLX-1 stands apart from the zoo of known astrophysical objects, stubbornly refusing to be categorized by the rules we've used for decades. When it was first detected in 2009, astronomers were struck by the sheer intensity of its X-ray output, something that couldn't be reconciled with the black holes they were familiar with. It was far too luminous to be powered by a small black hole, and yet, it lacked the hallmarks of a supermassive one. It was something in between, and that was where things got exciting. Located in the outskirts of its host galaxy, HLX-1 doesn't occupy a central, gravitationally dominant position like many supermassive black holes do. Instead, It lurks in the galactic halo, some 3,000 light-years from the nucleus of ESO 243-49. That's a strange place to find such a luminous object. Usually, the brightest X-ray emitters are in crowded, active regions, where stars are dying, where galaxies are colliding, or where supermassive black holes feed. But HLX-1 sits off-center, glowing furiously in a place that shouldn't be this interesting. And that anomaly, its location, immediately triggered speculation. Why is such a powerful source of energy sitting so far from the galactic core? The answer might be tied to its name. The hyperluminous part isn't just a fancy adjective. It's a classification. Astronomers define ultraluminous X-ray sources, ULXs, as non-nuclear X-ray sources with luminosities exceeding 10 to the power of 39 erg/s, which already surpasses the Eddington limit for typical stellar mass black holes. HLX-1, however, is in a league of its own. Its luminosity peaks around 10 to the power of 42 erg/s, roughly 100 to 1,000 times more powerful than the brightest ULXs. That places it in a new category altogether, hyperluminous X-ray sources. And HLX-1 was the first of its kind to be definitively recognized. This level of energy output can't be explained by standard models of accretion onto stellar mass black holes. If a black hole smaller than 100 solar masses were producing that much radiation, it would violate the Eddington limit so drastically that it would effectively blow away any material trying to fall in, cutting off the fuel supply. So unless some beaming effect is at play, where the X-rays are directed narrowly toward Earth, creating the illusion of higher brightness, the only plausible explanation is that HLX-1 is significantly more massive than a stellar mass black hole. Over time, deeper studies with X-ray observatories like XMM Newton, Chandra, and Swift reinforced the idea that this wasn't a fluke or a misidentification. HLX-1 was real, and it was powerful. It varied in brightness. It changed states. It followed patterns. And the way it behaved resembled smaller black holes in some ways, but scaled up, much larger, much stronger, and possibly much older. Its host galaxy, ESO 243-49, is a lenticular galaxy, a type of galaxy that sits somewhere between a spiral and an elliptical. It's not a particularly active or dramatic galaxy by cosmic standards. Yet on its outskirts blazes this strange object, HLX-1, like a lighthouse flashing across intergalactic darkness. If we didn't know better, we might think it was a small galaxy or a compact quasar, but its spectrum, its variability, and its distance from the galaxy's core all suggest otherwise. In short, HLX-1 is a unique cosmic entity, a hyperluminous X-ray source far outside the Milky Way, located in a galaxy most people have never heard of, but which may turn out to be one of the most important laboratories in the universe for studying black holes that don't fit neatly into our old classifications. It might not just be an oddity. It might be a cornerstone. Black holes come in many sizes, but most fall into two well-established camps. On one end of the scale are stellar mass black holes, formed from the deaths of massive stars. They typically weigh between about 5 and several dozen solar masses. On the opposite extreme are the supermassive black holes, millions to billions of times the mass of our Sun, anchoring the cores of galaxies, including our own Milky Way. These are well documented, observed through the motions of stars, the bending of light, and most dramatically, through the Event Horizon Telescope's image of the black hole in M87. But between these two familiar extremes, there's a curious emptiness, a mass gap that, for a long time, has seemed like a blank page in the black hole encyclopedia. That's where intermediate mass black holes, or IMHs, come in. Defined loosely as black holes with masses between about 100 and 100,000 times the mass of the Sun, IMHs are the missing link in black hole evolution. Theoretically, they should exist. Models of galaxy formation and black hole growth require them. After all, it's hard to imagine how supermassive black holes could grow to their titanic sizes in the early universe without passing through an intermediate stage. They either had to be born massive, which presents its own theoretical headaches, or they had to grow from something smaller, step by step. IMHs, then, are not just a curiosity, they're a necessity for cosmology to make sense. But here's the problem. Finding them has been like trying to catch fog in your hands. IMHs are elusive for several reasons. First, they don't form in the same way as stellar mass black holes. While we know that massive stars collapse under their own gravity at the end of their lives to form stellar black holes, the formation path of IMHs is far less clear. Some theories propose that IMHs could arise from repeated mergers of smaller black holes in densely packed star clusters. Others suggest they could form from the direct collapse of massive gas clouds in the early universe, bypassing the stellar stage altogether. Still others envision runaway collisions in young, massive star clusters, where massive stars slam into each other repeatedly, building up enough mass for a collapse directly into an IMH. But even if they do exist, they're incredibly hard to detect. Unlike their stellar mass cousins, IMHs are too big to form from individual stars, yet too small to command the bright, active centers of galaxies like supermassive black holes do. Most importantly, they don't necessarily announce their presence with powerful, continuous radiation. A stellar black hole in a binary system can shine brightly in X-rays as it devours a companion star. A supermassive black hole can light up an entire galaxy as a quasar. But IMHs? They might just sit in the dark, quietly lurking in globular clusters, wandering the outskirts of galaxies, or floating through intergalactic space, too dim, too remote, or too infrequently active for our instruments to catch. That's why candidates like HLX-1 are so crucial. They offer rare glimpses into this hidden population. They give us a flash of light, a spectral fingerprint, a behavioral pattern we can study. Before HLX-1, there were other candidates, such as M82X1, a powerful X-ray source in a nearby galaxy, but none with the clarity, regularity, and sheer luminosity that HLX-1 displayed. Most IMH candidates are tentative, with alternate explanations always hovering nearby. They might be beam sources. They might be unusually bright stellar mass black holes. They might even be supernova remnants masquerading as something more exotic. The ambiguity is constant. Even when we do find something suspicious, like a globular cluster with unusually fast-moving stars, drawing a firm conclusion is nearly impossible. Without the right signatures, without repeated observation across different wavelengths, it's easy to mistake noise for signal or to misidentify the nature of what we're seeing. Intermediate mass black holes are not just rare in number. They're rare in behavior. They seem to live quiet lives, emerging only during moments of dramatic activity, like sudden bursts of accretion, or tidal interactions with nearby stars. These moments are fleeting, and unless we catch them at just the right time, we miss the chance to learn anything. That's what made HLX-1 such a thrilling discovery. It wasn't just luminous, it was active, variable, and crucially, repeatable. It didn't just flash once and vanish. It came back, with a rhythm, a pattern, a behavior that could be tracked. In a universe where IMHs seemed more theoretical than real, HLX-1 walked out of the shadows and declared, "I exist." When astronomers talk about the universe, scale quickly becomes almost meaningless to the human mind. Light travels at nearly 300,000 kilometers per second, and yet even at that cosmic speed, it takes over 8 minutes just to reach Earth from the Sun. That's a single star in our local backyard. Now imagine an object that's not just a few light minutes away, or a few light years, but almost 300 million light years from us. That's where HLX-1 resides, a whisper of energy reaching us across a vast cosmic gulf, from a galaxy named ESO 243-49. ESO 243-49 is a lenticular galaxy, a type of galaxy that sits somewhere between a spiral and an elliptical in both structure and behavior. It doesn't have the dramatic arms of a spiral galaxy like the Milky Way, nor the featureless roundness of an elliptical galaxy. Instead, it's disc-shaped, smooth, and relatively quiescent, meaning it isn't actively birthing new stars at an aggressive pace. It lies in the southern constellation Phoenix, and under most circumstances, it would be an unremarkable galaxy among billions. But thanks to HLX-1, ESO 243-49 has become a cosmic laboratory, a place where one of the most compelling black hole candidates ever detected has taken up residence. What makes HLX-1 even more intriguing is that it doesn't sit at the center of ESO 243-49. It's located about 3,000 light-years away from the galaxy's core, well off to the side, embedded in the galactic halo. That detail is more than just geographical trivia. The position of HLX-1 breaks expectations. Supermassive black holes typically occupy the nuclei of galaxies, where the gravitational potential is deepest and gas and stars are plentiful. Stellar mass black holes, on the other hand, can appear throughout a galaxy, especially in regions of active star formation. But HLX-1's hyperluminous presence in a relatively quiet, outer region of a passive galaxy is like finding a campfire burning on the edge of a frozen wasteland. It begs an explanation. How did a black hole capable of generating such immense energy end up so far from the gravitational center of its host galaxy? One theory posits that HLX-1 is the core remnant of a smaller galaxy that was swallowed by ESO 243-49 in the distant past. In this scenario, a dwarf galaxy, complete with its own intermediate mass black hole, was gravitationally disrupted during a galactic merger. The black hole, and perhaps some residual stars that orbited it, were left in orbit around the larger galaxy, slowly settling into the halo region. The result is a lonely, displaced black hole that still manages to shine, thanks to its interaction with surrounding matter or perhaps a captured star that now feeds it. That off-center position has enormous implications for its identification. First, it rules out the possibility that HLX-1 is a supermassive black hole anchoring ESO 243-49. If HLX-1 were sitting directly in the galactic center, its luminosity might be dismissed as normal quasar activity, or attributed to a typical active galactic nucleus, AGN. But its position in the outskirts makes it something else entirely. It's not part of the main gravitational structure. It's a wanderer. A rogue source, fiercely bright and physically separate from the galactic engine room. This spatial dislocation also helps eliminate other common explanations for bright X-ray sources. It isn't located in a dense star-forming region where high-mass X-ray binaries, HMXBs, often appear. It isn't near the kind of nebulae where supernova remnants shine brightly in multiple wavelengths. Its position suggests isolation, possibly ancient, possibly the relic of an event long past, but active nonetheless. The location also makes HLX-1 an excellent candidate for long-term study. Because it's removed from the bright central regions of ESO 243-49, it's easier to isolate HLX-1's emissions from the background light of the host galaxy. This isolation allows for cleaner spectral data and better measurements across wavelengths, giving scientists a clearer look at its behavior without interference from other galactic noise. So here we have an object, not in the Milky Way, not even in the local group of galaxies, but hundreds of millions of light-years away, positioned like a cosmic outsider, blazing with a rhythm all its own. It's not just HLX-1's behavior that draws attention. It's the fact that it's where it shouldn't be, doing things it shouldn't do, in a place most astronomers wouldn't have thought to look. When HLX-1 first announced itself to astronomers, it didn't do so quietly. It didn't whisper across the cosmos or hide behind veils of dust. Instead, it screamed, in X-rays. The brightness of HLX-1 in the X-ray portion of the electromagnetic spectrum is one of the primary reasons it captured global attention. And this wasn't ordinary brightness. HLX-1 is what scientists call hyperluminous, meaning its X-ray output exceeds even the most energetic of typical ultraluminous X-ray sources, or ULXs. In raw figures, HLX-1 can shine with an X-ray luminosity peaking around 10 to the power of 42 ergs per second. For context, that is more than 1,000,000 times the X-ray luminosity of a typical stellar mass black hole in a binary system, and several hundred times brighter than even the most extreme ULXs. To the untrained eye, numbers like these may feel abstract, but they carry with them staggering implications. To shine that brightly in X-rays requires the conversion of massive amounts of matter into energy, and not just any energy, high-energy photons that suggest a deeply energetic process, accretion. This is the key, The radiation isn't just pouring out of HLX1 from nowhere. It's being generated by matter, gas, dust, maybe even stellar material, spiraling into the black hole and heating up through friction and gravitational compression to millions of degrees before crossing the event horizon. The result is a violent, high-energy storm of radiation. But again, not just any storm, this is a Category 10 hurricane of energy. What makes this particularly fascinating is the Eddington limit. This is a theoretical upper bound on how bright an object can shine due to accretion before the radiation pressure itself pushes incoming material away, halting the feeding process. In other words, if a black hole shines too brightly, it blows away the very fuel it needs to continue shining. For a stellar mass black hole, say, around 10 solar masses, this limit is about 10 to the power of 39 ergs per second. HLX1 is 1,000 times more luminous than that, which means if it were a stellar mass black hole, it would be violating the laws of physics as we understand them. Unless, of course, it's not stellar mass at all. The X-ray brightness of HLX1, therefore, isn't just an observational feature, it's a diagnostic tool, an astrophysical clue pointing to the object's likely mass. For HLX1 to remain within the bounds of the Eddington limit, and shine as brightly as it does, it would need to be about 10,000 solar masses. That places it firmly within the range of intermediate mass black holes, IMHs, a classification so rare, so poorly understood, and so long sought after that the very existence of HLX1 turned heads across the astronomical community. But the brightness is only part of the story. It's how HLX1 shines that adds further intrigue. For one, HLX1's X-ray emission isn't static. It varies over time, flaring up dramatically and then fading, in a repeating cycle roughly every 400 days. This rhythmic behavior, almost like a cosmic pulse, mimics the accretion cycle seen in stellar mass black holes found in X-ray binaries. These stellar systems experience outbursts when material from a companion star piles up in the accretion disk, then suddenly falls into the black hole, releasing a burst of energy. Afterward, they enter a quiescent state, when the inflow slows and the emission dims. HLX1 appears to do the same thing, but on a grander scale. Instead of minor fluctuations, it undergoes massive X-ray flares, each rising quickly and then fading slowly over weeks or months. This behavior is critical. It suggests that HLX1 isn't just a static X-ray emitter like a supernova remnant. It's a dynamic system, likely involving a binary companion that delivers material in a periodic, perhaps elliptical, orbit. Every time the companion star swings close to the black hole, tidal forces strip material from it, fueling a temporary feeding frenzy that ignites HLX1's luminosity. This repeatability also allows for consistent study. Rather than a one-off flare, HLX1 provides a sort of cosmic heartbeat, pulsing in X-rays in a way that scientists can anticipate and observe. That's invaluable. It means HLX1 is not only a candidate for an IMBH, it's a living laboratory, one where astrophysicists can test theories of accretion, black hole feeding mechanisms, and radiation dynamics on an entirely different mass scale. Even more compelling is the spectral state changes observed in HLX1. Like stellar mass black holes and binaries, HLX1 switches between different emission states, specifically, the hard and soft X-ray states. During the hard state, HLX1 emits high-energy photons and is relatively faint. During the soft state, it becomes much brighter, with lower-energy X-rays dominating the spectrum, usually associated with a well-formed, hot accretion disk. This behavior aligns with what's known from smaller black holes in our galaxy, lending weight to the idea that HLX1 is just a larger version of a known mechanism. Now, if HLX1 were merely beaming its X-rays toward us, if the light were artificially magnified by relativistic effects from a jet pointed directly at Earth, that could, in theory, explain the high brightness without invoking a high mass. But several lines of evidence work against that. For one, beam sources often show distinctive radio emissions and relativistic jets. HLX1, while not entirely silent in radio wavelengths, is remarkably faint. Additionally, its X-ray spectrum doesn't match what's expected from strongly beamed systems. That leads many researchers to conclude that HLX-1's luminosity is indeed isotropic, radiated in all directions, and not an illusion caused by a fortuitous viewing angle. HLX-1's X-ray brightness is thus not only extraordinary, but also uniquely informative. It allows researchers to infer not just how it behaves, but also what it must be. There are very few objects in the universe that can match this level of sustained, variable, and well-characterized high-energy output without being either supermassive black holes at galactic centers or temporary phenomena like gamma-ray bursts. HLX-1 stands alone, or nearly so, as the best candidate for something that has long existed only in theory, an intermediate mass black hole caught in the act of feeding. And perhaps that's what makes its brightness so special. It's not just about how much light it produces. It's about what that light tells us, that hidden among the galaxies, perhaps on the outskirts where few would think to look, like creatures of mass and power, too big to be born of stars and too small to rule galaxies, quietly burning in X-rays, daring us to notice. Measuring the mass of a black hole that sits 300 million light-years away is no simple task. Unlike nearby binary systems in our own galaxy, where individual stellar motions can be tracked, HLX-1 lies embedded in the outer halo of a distant galaxy, far beyond the resolution of direct dynamical measurements. And yet, even from that unimaginable distance, astronomers have been able to make a remarkably precise estimate of its mass, placing it in the range of around 10,000 times the mass of our Sun. That number is far from arbitrary. It's the result of years of careful observation, modeling, and cross-checking with physical laws that govern how black holes behave. It all begins with luminosity, especially in the X-ray spectrum. As mentioned previously, HLX-1 is a hyperluminous X-ray source, meaning its energy output is orders of magnitude greater than what we see from stellar mass black holes. The first red flag, or rather, golden flag, was its brightness, around 10 to the power of 42 ergs per second at peak. That's nearly 100 times brighter than the maximum theoretical output a 20 solar mass black hole could produce without exceeding the Eddington limit, the threshold at which radiation pressure pushes back on infalling matter and prevents further accretion. In simpler terms, if HLX-1 were a small black hole, say, 10 or 20 solar masses, its brightness would violate the known laws of physics unless the light was somehow being artificially boosted. But there's no evidence that HLX-1 is beaming its emissions in our direction, which rules out strong relativistic jets or orientation tricks. That leaves one obvious answer. The black hole is simply massive enough that its Eddington limit is naturally higher. To shine at the observed brightness without violating this limit, the object must be roughly 10,000 solar masses. And that's how we arrive at one of the most compelling mass estimates for any candidate in the intermediate mass category. But luminosity alone isn't enough to clinch the argument. Astronomers needed more. So they turned to the spectral state transitions HLX-1 undergoes during its periodic X-ray flares. These transitions, between the hard and soft states, are commonly seen in stellar mass black hole binaries, where they provide a window into the structure and temperature of the accretion disk. As HLX-1 flares, its spectrum becomes dominated by softer, lower-energy X-rays, which is interpreted as the thermal emission from a very hot inner accretion disk. By modeling the shape of this thermal spectrum, astronomers can estimate the radius of the innermost stable circular orbit, or ISCO, which is essentially the closest material can orbit a black hole without plunging in. And here's where general relativity becomes a cosmic yardstick. The ISCO's size depends on the mass of the black hole. It scales linearly. Larger black holes have proportionally larger ISCOs. From HLX-1's soft-state spectra, scientists deduced that the accretion disk was too large to be orbiting a typical stellar mass black hole. The thermal profile suggested a disk consistent with a black hole in the thousands of solar masses range. This served as a second independent line of evidence, supporting the luminosity-based estimate. A third approach involves using the outburst decay times, how long it takes HLX-1 to fade from its peak X-ray brightness back into quiescence. In stellar mass X-ray binaries, this decay is closely tied to how much mass the disk contains, which in turn is influenced by the black hole's mass. HLX-1's decay times are too long to be explained by a low-mass black hole with a small disk. Instead, they align beautifully with the expected behavior of a massive disk around an intermediate mass object. In essence, HLX-1's feeding frenzies last longer and are more drawn out because its accretion disk is more massive and more extensive, a natural consequence of a more massive black hole at the center. Even more sophisticated modeling, combining X-ray data with optical and ultraviolet observations, allowed scientists to estimate how much matter is being accreted and how efficiently it's converted to energy. These calculations also suggest a black hole too large to be explained by the deaths of individual stars. It would be nearly impossible for a single stellar collapse to create such an object. That rules out standard black hole formation models and leads us directly to the intermediate mass range. Moreover, if HLX-1 truly weighs in at around 10,000 solar masses, then it perfectly fits into a long-sought and sparsely populated range. Until HLX-1, the black hole zoo had two main categories: stellar mass black holes, from a few to a few dozen solar masses, and supermassive black holes, millions to billions of solar masses, found in the centers of galaxies. Between them lies a yawning chasm, with few confirmed residents, despite theoretical expectations that intermediate mass black holes should exist. HLX-1 stands right in that gap. It's not massive enough to be mistaken for a galactic nucleus, and it's far too massive to have formed from a typical supernova. That makes it the best IMBH candidate to date. There's also a broader implication to HLX-1's estimated mass. It may be a building block for supermassive black holes. One of the great mysteries in astrophysics is how the giant black holes at the centers of galaxies grew so quickly in the early universe. Some theories suggest they started out as intermediate mass black holes that merged or accreted matter over billions of years. HLX-1 could be a living fossil, a survivor of that early phase of cosmic evolution, giving us a glimpse of what the precursors to galactic giants might have looked like. Still, it's important to note that mass estimates, while robust, come with uncertainties. Modeling accretion disks across vast distances involves assumptions about inclination angles, disk structure, and radiative efficiency. Slight variations in those assumptions could shift the estimated mass by a factor of 2 or more. But even at the low end, HLX-1 still lands well above the stellar mass threshold, preserving its status as a true intermediate mass candidate. In short, HLX-1's estimated mass is not just a number. It's the synthesis of a story told in brightness, in spectral shape, in timing, and in comparison to every other black hole we've seen. It's a number that pushes HLX-1 into a rare and potentially foundational class of objects, one that links the smallest black holes born from stars to the monstrous engines that power quasars and active galactic nuclei. In this delicate bridge between extremes, HLX-1 stands tall, glowing not just with energy, but with significance. In the vast darkness of space, discovery often begins not with a bang but with a quiet anomaly, an unexplained brightness, a blip in the data, a dot where none was expected. HLX-1 entered the astronomical stage in exactly that manner, not with fanfare but with curiosity. It was 2009, and the European Space Agency's Newton Space Observatory had been steadily scanning the X-ray universe, compiling data from across galaxies and star clusters, searching for sources of high-energy radiation that could hint at exotic phenomena like black holes, neutron stars, or supernova remnants. Then, something caught the eye of astrophysicist Sean Farrell and his team. While analyzing archival data from Newton, they noticed an extraordinarily bright X-ray source located not within the disk of a galaxy, but hovering just outside the plane of a spiral galaxy known as ESO 243-49. This source was unlike the many other X-ray emitters typically found within galactic centers or stellar remnants. It was too far offset, too bright, and too persistently luminous to be ignored. It wasn't initially christened HLX-1. That name, Hyperluminous X-ray Source 1, would come after confirmation and further study. In the beginning, it was a question mark, a blinking outlier in an ocean of data. But it stood out in its sheer X-ray intensity, putting out as much energy as 240 million suns in the X-ray spectrum alone. It was the brightest known off-nuclear X-ray source at the time, something that instantly raised eyebrows. The source wasn't located in the bright heart of ESO 243-49, which could have suggested a supermassive black hole, nor was it positioned within a globular cluster or any dense stellar nursery. Instead, it resided in the outer halo of the galaxy, an unusual neighborhood for such immense energy output. That positioning raised an important possibility. Could this be an intermediate mass black hole in the process of accreting material? To find out, astronomers began to piece together the full story of its detection. The original data from XMM Newton's EPIC, European Photon Imaging Camera, showed a remarkably consistent brightness, peaking in the soft X-ray band, an energy range often associated with accretion disks around black holes. But to understand the full picture, the team didn't stop at one snapshot in time. They dug into multiple epochs of archival data, reanalyzing previous observations from different telescopes to track how this source had behaved over months and years. After flagging the object as a hyperluminous X-ray source, they coordinated follow-up observations with other space-based observatories, including NASA's Swift and Chandra X-ray Observatory. These telescopes provided crucial supplementary data, especially regarding the variability of HLX-1's emissions. Variability in X-rays is a telltale sign of black hole accretion activity. Unlike supernova remnants or stable neutron stars, accreting black holes tend to flicker and flare as they consume matter. And HLX-1 did just that. The Swift X-ray Telescope, XRT, showed that HLX-1 wasn't a constant emitter. Instead, it underwent outbursts every roughly 400 days, rising and falling in intensity in a cyclical pattern. This discovery was crucial. Not only did it support the black hole interpretation, but the pattern of variability was also strikingly similar to what we see in known stellar mass black holes and binary systems, just scaled up in energy and timescale. That gave astronomers yet another piece of the puzzle. HLX-1 was behaving like a larger version of a known system, but with vastly more power. In addition to these high-energy observations, researchers sought to understand the environment around HLX-1 by turning to optical and ultraviolet telescopes, including the Hubble Space Telescope. These observations confirmed the location of the source near ESO 243-49 and detected a faint optical counterpart, likely a cluster of young stars surrounding the black hole. This counterpart helped further rule out the possibility that HLX-1 was just a background quasar or a foreground object in our own galaxy. The redshift measurements from the optical data placed HLX-1 squarely in the neighborhood of ESO 243-49, confirming its extragalactic nature. What began as a data anomaly quickly matured into one of the most exciting astrophysical discoveries of the decade. HLX-1 was confirmed not just as a random X-ray flare or a misidentified star, but as a stable, recurring source of intense X-ray emissions, a black hole candidate with mass estimates and behaviors entirely consistent with the elusive intermediate mass class. In the subsequent months and years, HLX-1 would become the focus of intense study, a kind of gravitational celebrity around which entire campaigns of observation were launched. To give you a sense of how remarkable its detection was, consider this. Before HLX-1, the existence of intermediate mass black holes was still largely theoretical. There were candidates, of course, off-nuclear X-ray sources in other galaxies, for example, but most lacked the kind of multi-wavelength data and repeated flaring activity that HLX-1 exhibited. HLX-1, by contrast, could be monitored, modeled, and predicted. Its discovery didn't just fill a theoretical gap, it opened a doorway into a new subfield of astrophysics. The detection also illustrated the power of archival data mining. HLX-1 was sitting in the data all along, waiting to be noticed. Without the keen eye of researchers combing through massive datasets, it might have remained undiscovered for years. And once it was found, a whole suite of instruments, both space-based and ground-based, rallied to its cause. It became a rare example of how collaborative, multi-observatory efforts can transform a distant flicker into a landmark discovery. To this day, HLX-1 remains a beacon for intermediate mass black hole research. Its detection story is not just about instruments and photons, it's about persistence, about curiosity, and about the immense rewards that await when the universe decides to reveal one of its secrets. From a whisper in the data to a confirmed candidate in the black hole family tree, HLX-1 was not just detected, it was uncovered, validated, and enshrined in the catalog of cosmic wonders. Black holes, though often lumped together in the popular imagination as simply cosmic vacuum cleaners, actually exist in a striking variety of sizes, and each class carries vastly different implications for how the universe evolves. To truly understand why HLX-1 is so special, we must place it within this broader hierarchy. It's not just another black hole. It's a black hole that dares to exist between the two best established categories, stellar mass black holes and supermassive black holes. This in-between status, this intermediate mass, is what makes HLX-1 both fascinating and so rare. Let's begin with the familiar. Stellar mass black holes are the end products of massive stars, those that begin their lives at 8 or more times the mass of our Sun. When these stars exhaust their nuclear fuel, they collapse under their own gravity, triggering a supernova and leaving behind either a neutron star or a black hole. The resulting black holes generally have masses ranging from about 3 to 20 solar masses, although a few have been found at the upper end around 50 to 100 solar masses, especially thanks to gravitational wave detections by LIGO and Virgo. At the other extreme, we have supermassive black holes, gravitational monsters that lurk at the centers of galaxies, including our own Milky Way. These beasts range from millions to billions of times the mass of the Sun. They govern the dynamics of their host galaxies, powering quasars and other luminous active galactic nuclei when actively accreting matter. Their sheer size, influence, and visibility make them comparatively easier to detect despite their incredible distances. But between these two extremes lies a curious and persistent gap: intermediate mass black holes, or IMHs. Their mass range is roughly defined as between 100 and 100,000 solar masses, too massive to be formed by the death of a single star, and far too small to be classified as a supermassive black hole. They are the missing middle, the long-sought link in the cosmic evolutionary chain. And yet, the universe has been frustratingly stingy with evidence of their existence. That's why HLX-1 matters. It fits right in this intermediate category, with mass estimates centering around 10,000 solar masses, placing it smack in the sweet spot where very few other confirmed candidates exist. And that makes it both scientifically precious and deeply enigmatic. Its mass is too high to be explained by a single supernova event. No known stellar process can create a black hole this massive. At the same time, it's far too small and too isolated to be considered a supermassive black hole in the traditional sense. It doesn't sit in the heart of a galaxy or anchor the swirling core of a galactic disk. Instead, it resides in the outskirts of galaxy ESO 243-49, perhaps even a remnant of a dwarf galaxy itself. So what makes it intermediate? The answer lies not only in its mass but in its behavior and environment. Compared to stellar mass black holes, HLX-1 emits far more energy, particularly in the X-ray spectrum. It undergoes periodic flaring activity, just like smaller black holes in binary systems, but these flares are orders of magnitude brighter and operate on a longer timescale. Stellar black holes might flare up over a few days or weeks. HLX-1's outbursts span hundreds of days, suggesting a much larger accretion disk and a stronger gravitational well. And yet HLX-1 doesn't behave like a supermassive black hole either. It lacks a surrounding galactic bulge. It doesn't power a blazing quasar or shoot relativistic jets thousands of light-years long. There's no vast accretion torus or galaxy-wide radiation signature. It's not central to anything, it's peripheral, a wanderer in the outskirts. Its intermediate behavior mirrors its intermediate size. It doesn't just bridge the gap, it defines it. This middle ground status also poses a deeper puzzle about black hole formation itself. If stellar mass black holes form from collapsing stars, and supermassive ones grow by accreting matter or merging with other black holes over billions of years, then where do intermediate mass black holes like HLX-1 come from? Did they form directly from the collapse of primordial supermassive stars in the early universe, Giants that lived and died before galaxies even coalesced? Did they grow gradually from mergers of smaller black holes, piling up over cosmic time in dense star clusters? Or, more provocatively, are they stripped cores of dwarf galaxies consumed by larger hosts, a galactic fossil, if you will? HLX-1 provides tantalizing clues to all these questions. Its mass is large enough to suggest an ancient origin, perhaps dating back to the early universe. But its location, offset from the center of its host galaxy, hints at a more complex story. Could HLX-1 be a leftover, a black hole that once anchored its own small galaxy, which was later cannibalized by ESO 243-49? That would not only explain its mass but also its position and surrounding young star cluster. To underscore just how precious HLX-1 is, consider this: despite decades of searches, very few credible IMBH candidates have been identified. Other possible IMBHs, such as those inferred from ultraluminous X-ray sources, ULXs, or dense star clusters, lack the clear, consistent observational signatures that HLX-1 provides. Some may be explained by beaming effects or stellar mass black holes with unusually high accretion rates, but HLX-1 refuses to be simplified. Its mass estimate is robust, its variability pattern is clear, and its spectral behavior mimics black holes, just scaled up in every way. It's not quite like the small ones. It's not quite like the giants. It is the in-between, a cosmic adolescent caught between birth and full maturity. This in-between status is what makes HLX-1 not just another point of light in the sky, but a fundamental key to understanding how black holes evolve, grow, and shape the universe. The intermediate class may be rare, but with HLX-1, we've found a shining example, brighter than most, heavier than expected, and perfectly placed to answer one of the great cosmic riddles: how do black holes grow up? Accretion is the lifeblood of an active black hole. It's not just what makes them visible, but what allows us to study their otherwise invisible presence. For HLX-1, this process is more than just a theoretical construct. It's the very mechanism that makes this intermediate mass black hole candidate stand out in the cosmic crowd. What sets HLX-1 apart is not just its brightness, but the rhythm and consistency of its emissions. Its behavior echoes the known physics of X-ray binaries, but with a twist: it does it all on a dramatically larger scale. In typical X-ray binaries, we observe a stellar mass black hole or neutron star gravitationally bound to a normal star, often a massive or evolved one. As the companion star orbits the compact object, its material is pulled in through a process known as Roche-Lobe overflow or stellar wind capture, depending on the system. This infalling matter spirals into the black hole, forming a hot, spinning accretion disk that heats up to millions of degrees. That's where the high-energy X-rays come from, matter getting compressed, superheated, and accelerated just before it disappears beyond the event horizon. HLX-1, intriguingly, behaves in a remarkably similar fashion. It exhibits periodic changes in X-ray luminosity that are consistent with the accretion cycles observed in known black hole binaries, albeit with some significant differences in scale and duration. For one, HLX-1's outbursts last longer, and the period between them, about 400 days, is much greater than the short weeks or months typically observed in stellar systems. These patterns suggest that HLX-1 is accreting material from a companion star in an eccentric orbit, likely coming close enough only once every 13 months to transfer a significant amount of matter. When that happens, HLX-1 lights up like a flare in deep space. The accretion disk swells, the inner regions become superheated, and the X-ray output spikes dramatically. This event, an accretion-driven outburst, is a cosmic feeding frenzy, and it's key to understanding HLX-1's true nature. Just like smaller black holes, HLX-1 appears to go through spectral state transitions as it feeds. It moves between a low/hard state, where emissions are dominated by higher energy X-rays possibly produced by a hot corona, and a high/soft state, where the emission peaks in softer X-rays and is dominated by thermal radiation from the inner accretion disk. These transitions are not just cosmetic, they are deeply diagnostic. The way a black hole changes its X-ray spectrum reveals what's happening in the extreme environment near the event horizon. And in HLX-1's case, these shifts mirror what's seen in much smaller systems, offering compelling support for the idea that black holes of all sizes follow similar physics. The difference lies not in the fundamental processes, but in the scale. HLX-1 is an X-ray binary on cosmic steroids. What's more, the rate at which HLX-1 brightens and dims during these cycles is too fast to be explained by a supermassive black hole. Larger black holes have longer characteristic timescales because of their sheer size. Light takes more time to travel around their accretion disks, and infalling matter takes longer to reach the event horizon. The fact that HLX-1 can switch between states on the order of days to weeks strongly supports the idea that it's much smaller than a supermassive black hole, another tick in the column for an intermediate mass identity. There's another curious feature to HLX-1's accretion activity. It appears to have a quasi-regular heartbeat. Every 400 days, like clockwork, the system flares up. This kind of periodicity is rare and hints at a structured interaction with the donor star, one that is not tightly bound in a circular orbit, but instead sweeps in close during periastron and dumps a load of gas into HLX-1's gravitational grip. The eccentricity of this orbit might explain why the system goes quiet for so long between outbursts, and then erupts with activity as the star swings close again. Moreover, the consistency and repeatability of these flares gives scientists an unprecedented opportunity to model the physics of the system with remarkable precision. They can predict when the next flare is likely to occur, observe it in real time across multiple wavelengths, and then analyze the changes in spectral state, luminosity, and disk temperature. This data allows for detailed comparisons with known X-ray binaries and adds yet another layer of credibility to HLX-1's IMH classification. Interestingly, even the total energy output during these flaring episodes follows a similar pattern to that seen in stellar systems. The Eddington luminosity, the maximum luminosity a black hole can achieve when radiation pressure balances gravitational pull, scales directly with mass. And in HLX-1's case, the peak luminosity fits neatly with the predicted Eddington limit of a black hole weighing in at about 10,000 solar masses. This again underscores that HLX-1 is not simply a more active stellar mass black hole or a faint supermassive one. It lives in the intermediate zone in both behavior and power. One of the more profound implications of HLX-1's accretion activity is how it serves as a microcosm of black hole feeding processes. If black holes this size behave like scaled-up versions of stellar X-ray binaries, then perhaps supermassive black holes evolved through similar steps, gradually merging and growing from these intermediate ancestors. HLX-1 becomes more than a curiosity. It becomes a template, a living fossil of black hole growth. This accretion activity also opens the door to future studies in accretion disk dynamics, relativistic jet formation, even if HLX-1 lacks significant jets, which we'll explore later, and the interplay between companion stars and massive compact objects. It allows researchers to test theoretical models under conditions that can't be recreated in smaller systems. In the end, HLX-1's accretion behavior isn't just mimicry. It's a larger-scale reiteration of universal black hole principles. It speaks the same language as the tiny black holes scattered through our galaxy, but does so with a deeper voice and a broader reach. This mirroring reinforces the belief that black holes, no matter their mass, follow the same fundamental rules of engagement with matter. HLX-1 just operates on a stage big enough to show those rules with unparalleled clarity. The recurring flare cycles of HLX-1 are among its most intriguing and defining features, cosmic pulses that seem to mimic a kind of heartbeat in the void of deep space. These outbursts, occurring approximately every 400 days, are not random acts of chaos but rhythmic displays of gravitational feeding, suggesting a regular and structured interaction between the black hole and a potential companion star. The consistency of these cycles makes HLX-1 stand out even more in the sparse landscape of intermediate mass black hole candidates, offering researchers a rare opportunity to study black hole behavior with a predictability more often seen in stellar binaries. Every cycle begins with a sudden spike in X-ray luminosity. HLX-1 flares to life, its emissions climbing to astonishing levels. These outbursts last for several weeks to a couple of months before gradually declining, entering a quieter phase known as quiescence. Then, like clockwork, Around 13 months later, the entire process repeats. It's this remarkable periodicity that led scientists to suspect a very specific mechanism was at play, a companion star in an elongated, or eccentric, orbit that approaches HLX-1 at close range only once per orbit. When this companion star swings close to the black hole during periastron, the point in its orbit where it is nearest, tidal forces become overwhelming. HLX-1's immense gravity siphons off material from the star, pulling gas and stellar debris into its accretion disk. This sudden influx of mass ignites the flare, increasing the accretion rate and causing the X-ray brightness to skyrocket. It's a violent but ordered feeding event, almost like a cosmic heartbeat, regular, powerful, and revealing. This heartbeat analogy isn't just poetic. It has deep implications for astrophysical modeling. HLX-1 is one of the very few known black holes, especially among IMHs candidates, that shows this kind of consistent, large-scale behavior. Many other black holes, especially those suspected to be intermediate in mass, emit X-rays intermittently or remain persistently bright, but without a repeating flare pattern. HLX-1's cycle, on the other hand, is reliably periodic, making it a rare testbed for theoretical models of accretion behavior in massive compact objects. What's especially remarkable is how closely these flare cycles mimic those seen in stellar mass X-ray binaries. In those systems, a similar process occurs. A companion star loses mass to the black hole or neutron star, triggering X-ray outbursts. The difference is one of scale. HLX-1 is doing the same thing, but its flare strength and period are significantly larger. The emission during a typical HLX-1 outburst can reach luminosities in excess of 10 superscript 2 erg/s, several hundred times brighter than standard stellar black hole binaries. These luminosity peaks are consistent with Eddington-limited accretion, meaning that HLX-1 is pulling in as much material as gravity allows before radiation pressure pushes back. Moreover, the spectral changes during each flare cycle add another layer of depth to our understanding. HLX-1 transitions from a low/hard state, characterized by harder X-rays and lower overall luminosity, to a high/soft state during the outburst, where the emissions become dominated by softer thermal radiation. This spectral evolution matches what we see in other accreting black holes, reinforcing the conclusion that HLX-1 is behaving like a scaled-up version of a known phenomenon. But why the 400-day period? That duration gives crucial hints about the orbital parameters of the hypothetical companion star. A highly eccentric orbit explains why the black hole only accretes large amounts of material once per cycle. The star spends most of its time at a safe distance, only grazing the black hole's influence when it dips into its gravitational well at closest approach. This model is supported by the sharp onset of the flares and their comparatively rapid decline. If the orbit were more circular, the accretion might be more constant and less dramatic. Interestingly, the companion star doesn't appear to be entirely destroyed by the black hole's appetite. It must be massive and dense enough to survive repeated close encounters, although it likely loses a significant amount of mass during each pass. Over time, this star could be completely consumed, or it might spiral inward due to gravitational interactions, shortening the flare period or changing the system dynamics altogether. These flare cycles also offer a window into the long-term evolution of the system. Scientists are watching closely to see if the timing or intensity of the flares begins to drift over time, which could indicate changes in the orbit, mass transfer rate, or even signs of the system approaching a more dramatic transformation, such as the companion being entirely disrupted. So far, while there have been some irregularities in the timing and intensity, the 400-day cycle remains remarkably stable, suggesting a finely tuned interaction between two very unequal partners, a massive black hole and a resilient star. HLX-1's flare cycles do more than illuminate the black hole itself. They also shed light on the physics of accretion at larger scales, the nature of compact object binaries beyond our galaxy, and the mechanisms by which black holes grow. These regular outbursts provide not just energy and light, but information, each flare a chapter in an unfolding story of gravity, destruction, and cosmic recycling. And there's one more layer of importance. HLX-1's recurring flare cycle provides predictable windows of observation. most black holes don't grant that luxury. Astronomers often must wait for chance outbursts or rely on steady-state emissions that lack variability. But with HLX-1, scientists can prepare, coordinate instruments across X-ray, optical, and ultraviolet bands, and capture each stage of the cycle. This ability to plan ahead makes HLX-1 one of the most scientifically valuable IMBH candidates in the cosmos. So these flares, these 400-day heartbeats, aren't merely pretty light shows in deep space. They are the steady, pulsing signature of a black hole in action. They are evidence of structure amid chaos, and they offer a unique clockwork mechanism by which we can trace the rhythm of an otherwise invisible monster. HLX-1, through its recurring bursts, reveals itself not as a passive dark body in the sky, but as a dynamic system full of energy, activity, and story. The rhythmic flares of HLX-1 are more than just bright bursts in the dark. They are crucial pieces of evidence pointing to a deeply dynamic system, one in which the black hole is actively feeding on a companion star. And this feeding is not passive or steady, it's dramatic, episodic, and intimately tied to the gravitational dance between two celestial bodies. To understand why this matters, we must dig into the implications of such regular outbursts, and what they tell us about the nature of HLX-1. First, the flares suggest an ongoing interaction. Black holes don't emit light on their own. They're dark, by definition, and only become visible when they interact with matter. HLX-1's X-ray outbursts, periodic, powerful, and sustained, are direct indicators that it's consuming material, not as a one-off event, but as part of a repeating cycle. This hints at a stable, long-term relationship between HLX-1 and a donor star. That relationship likely involves an orbit, probably eccentric, that periodically brings the star close enough to the black hole for material to be stripped away and devoured. Such interactions are well understood in the context of X-ray binaries, where a compact object, typically a neutron star or a stellar mass black hole, accretes matter from a companion star. HLX-1 appears to follow this model, but at a much grander scale. What's particularly telling is how the timing of HLX-1's flares aligns so well with the theoretical orbital period. The 400-day interval isn't arbitrary. It fits perfectly with what we'd expect from a companion in an elongated orbit, where it's only close enough to transfer material during its periastron passage. This consistency builds a compelling case for a scenario in which the companion star is losing mass in bursts. When it nears HLX-1, tidal forces and gravitational stresses become intense. If the star fills its Roche lobe, or even if strong winds are being pulled off its surface, material can flow toward the black hole. This forms or replenishes an accretion disk, heating to millions of degrees and emitting X-rays as the gas spirals inward. And it's not just the existence of the flares that's important, it's how HLX-1 behaves during them. The transition between low and high spectral states, the shape of the light curve, and the energy distribution during each flare all point to the physics of accretion. These are not stochastic gamma-ray bursts or isolated supernova-like events. They are thermally driven, disk-mediated accretion phenomena, just what you'd expect from a black hole being periodically fed. What makes this even more compelling is that the flares are not uniform. Some are brighter than others, and some decline faster than the previous ones. This variability adds complexity and realism to the companion star model. It suggests that the mass transfer rate changes over time, perhaps due to alterations in the star's orbit, atmospheric conditions, or response to earlier interactions. In essence, the black hole's behavior is telling us a story about the companion as well, about how it's being affected by the repeated gravitational encounters. This kind of real-time evidence is invaluable because it allows astrophysicists to build predictive models. If HLX-1 is indeed accreting from a donor star, we can use the timing and intensity of the flares to estimate orbital elements, mass transfer rates, disk formation dynamics, and more. We can simulate different stellar types, giants, main sequence stars, or even stripped helium cores, and test which ones best match the observed behavior. These feeding events also provide key insights into the growth of black holes. One of the biggest open questions in astrophysics is how black holes, especially intermediate and supermassive ones, gain their mass. Are they born big? Do they merge from smaller black holes? Or do they grow slowly, over billions of years, by accreting mass from their environments? HLX-1 gives us a direct look at this process in action. It's not a relic or a dead remnant, it's actively consuming, evolving, and changing in real time. Moreover, the fact that HLX-1's feeding is episodic implies that the system may be in a transitional state. This could represent a phase in which a dwarf galaxy, potentially the one that brought the IMHs into ESO 243-49, is being stripped of its stars, one by one. HLX-1 could be consuming the stellar remains of its original host, or maybe just one unlucky survivor. The flares are then a cosmic signature of a galaxy's slow cannibalization, with the black hole as the final beneficiary. The importance of these flares extends even further. Since they are predictable, they allow for coordinated multi-wavelength observations. Astronomers can plan to observe HLX-1 in X-rays, optical, UV, and even radio, capturing each flare from multiple angles. This multispectral approach lets scientists track how matter behaves across different temperatures and distances from the black hole. It's a rare chance to watch a black hole turn on, feed, and dim, all with the timing of a ticking clock. Lastly, this regular feeding behavior helps differentiate HLX-1 from other types of bright X-ray sources that might otherwise be misidentified. Ultraluminous X-ray sources, ULXs, for instance, are often suspected to be stellar mass black holes or neutron stars accreting at super-Eddington rates. But those systems don't typically show this kind of long-period, high-intensity, recurrent outbursts. HLX-1's behavior is unique, and that uniqueness is precisely what supports its classification as an IMH. In short, the flares matter because they are evidence of life, of activity, of interaction, of a black hole not isolated in the dark but part of a larger, evolving system. They matter because they allow us to measure, to predict, and to understand. And they matter because they tell us we're witnessing something rare, an intermediate mass black hole, in the act of growing, showing us in real time how the cosmic engines of gravity, mass, and energy work on scales both familiar and profoundly vast. The theory that HLX-1 is being fed by a companion star in an eccentric orbit is one of the most fascinating and plausible explanations for its unusual, recurring outbursts. It adds a compelling narrative to the observations, a black hole and a star locked in a deadly dance, one that stretches across space and time, resulting in spectacular cosmic displays every 13 months. This idea doesn't just give us a way to explain HLX-1's behavior. It also opens a window into the inner workings of black hole feeding mechanisms, gravitational dynamics, and the long-term fate of such binary systems. To understand the theory in depth, let's start by considering what the data tells us. HLX-1 flares up in X-rays roughly every 400 days, in a pattern that's too regular to be random. This repeatability is a strong indicator of an orbital process. Something must be approaching the black hole on a schedule, depositing matter into its gravitational maw. The only plausible candidate is a companion star, possibly the remnant of a small dwarf galaxy that was long ago absorbed by the host galaxy ESO 243-49. In this model, the star is not orbiting HLX-1 in a neat circle like the Earth around the Sun. Instead, it follows a highly eccentric elliptical orbit, bringing it very close to the black hole at one end, periastron, and flinging it much farther away at the other, apastron. This elongated path means the black hole doesn't have constant access to the star's matter. It must wait for the star to return on its next close pass. When the star finally swings near, tidal forces stretch and distort it. If the star crosses its Roche limit, the black hole's gravity overcomes the star's self-gravity at the outer layers, pulling streams of gas and plasma into an accretion disk. This sudden surge of mass is what triggers the flare in X-ray emissions. There's more to the theory than just the timing of the flares. The way the light changes during each flare, the so-called spectral state transitions, mirrors what we see in stellar mass black hole binaries that are actively accreting. During the flare, the X-rays become softer, indicating that the material in the disk is heating up and becoming more optically thick. As the flare subsides, the spectrum hardens again, showing us that the accretion rate is falling. This behavior is not consistent with random, or one-time feeding events like a single star being disrupted. It is highly indicative of repetitive, partial mass transfer, exactly what you'd expect from a donor star in a repeating orbit. This model also helps explain why HLX-1 is not continuously bright. If the star orbited HLX-1 in a circular path close enough to transfer material all the time, we would see steady X-ray emission, not bursts. Instead, the periods of quiescence between flares suggest that for most of the orbit, the companion star is too far from the black hole to contribute significant material. Only during that brief, critical window at periastron does the black hole have the opportunity to feed. This explains the flare cycle's regularity and duration with beautiful simplicity. Now, what kind of star could survive such an arrangement? It would have to be dense and resilient, capable of enduring repeated gravitational encounters without being torn apart. Some researchers propose that the donor might be a helium star, the core remnant of a stripped-down stellar giant, or perhaps a main sequence or subgiant star. The key is that it must be massive enough to sustain multiple interactions without being completely disrupted, yet loose enough in its outer layers to allow for tidal stripping. Adding to the intrigue is the asymmetry in the flares. The rise is often steeper than the fall, suggesting a rapid injection of material followed by a slower, decaying accretion process. This kind of behavior is also seen in classical X-ray transients, where accretion disks go through thermoviscous instabilities. It's possible that once the donor star supplies a burst of gas, the accretion disk takes time to process and consume the material, resulting in a drawn-out emission profile. The eccentric orbit theory also dovetails neatly with the formation history of HLX-1. If the black hole is indeed the remnant of a stripped dwarf galaxy, the companion star could be the leftover nucleus or a core star from that galaxy. This would not only explain the black hole's intermediate mass but also its unusual position within ESO 243-49, off-center and not located at the galactic nucleus. It's almost as if HLX-1 and its companion are survivors of a cosmic collision, now orbiting together in a slow, fateful spiral. Moreover, this theory offers potential predictions. For instance, if the orbit of the companion star is slowly decaying due to gravitational radiation or dynamical friction within the galaxy, the flare cycle could begin to shorten over time. This is something astronomers can monitor in future observations. Similarly, if the donor star is gradually being eroded by the black hole's gravity, its mass loss rate may accelerate, causing changes in flare brightness or duration. These possibilities make HLX-1 a living laboratory for studying binary dynamics on extreme scales. Finally, this model provides an excellent opportunity for testing binary evolution theories. Systems like HLX-1 are incredibly rare, and we don't often get to observe an intermediate mass black hole paired with a visible stellar companion. This combination offers a new frontier in understanding how binary systems involving black holes evolve, how stable such interactions are, and what the ultimate fate of such systems might be. Could the companion eventually spiral inward and be destroyed completely? Could it trigger a runaway accretion phase that would allow HLX-1 to grow into a supermassive black hole over cosmic time? These are not just speculative questions, they are directly addressable by the companion star theory, and by future observations of HLX-1. The theory gives us a working hypothesis to test, a framework to refine, and a reason to keep watching, year after year, as the black hole continues its cosmic consumption cycle. Among the most fascinating behaviors exhibited by HLX-1, behaviors that closely tie it to familiar, smaller black holes, is its capacity for spectral state changes. These shifts are not random, nor are they isolated. They mirror, with eerie similarity, the behaviors observed in stellar mass black hole binaries right here in our own galaxy. And that mirroring is crucial. It strengthens the argument that HLX-1 is not some unusual outlier or exotic anomaly, but a genuine intermediate mass black hole undergoing the same processes we already understand on a smaller scale, just magnified. In black hole astrophysics, spectral states refer to different regimes of X-ray emission observed during phases of accretion. Broadly speaking, there are two dominant states, the low/hard state and the high/soft state. These names describe both the intensity and the energy distribution of the X-rays. In the low/hard state, the black hole's emission is dominated by high-energy, or hard, X-rays. This typically occurs when the accretion rate is low, and the accretion disk is thin, hot, and truncated far from the event horizon. In the high/soft state, however, the emission is dominated by lower energy, or soft, X-rays, indicating that the disk is thick, cooler, and extends closer to the black hole's surface. Now here's where HLX-1 becomes truly exceptional. Over multiple observational campaigns, HLX-1 has been seen transitioning between these two spectral states in a way almost indistinguishable from known stellar mass X-ray binaries. For example, as HLX-1 enters one of its flare cycles, the X-ray spectrum shifts dramatically, from a hard, power law-dominated shape to a soft, thermal disk blackbody signature. That change isn't just cosmetic. It means the physical structure of the inner accretion disk is altering as more matter is pulled in. The disk grows, spreads inward, heats up, and glows with softer, more intense X-rays. Just like in stellar systems, the transition to the soft state is typically accompanied by a sharp rise in brightness, indicating a spike in the accretion rate. HLX-1 essentially wakes up from a relatively quiet phase, rapidly ingests new material, and begins to shine more efficiently. These phases can last weeks to months and exhibit decay profiles similar to the fading tail of a stellar black hole's flare. Then, as the accretion disk runs out of fuel or stabilizes at a lower rate, HLX-1 transitions back to the hard state, emitting harder X-rays as the inner edge of the disk recedes. This cycle is not hypothetical, it's been observed and tracked. The European Space Agency's XMM Newton, NASA's SWIFT, and even Chandra X-ray Observatory have all participated in chronicling HLX-1's behavior. The black hole has now undergone multiple full-state transitions, each corresponding to a new flare. And it's not just the spectral shape that changes, the timing properties do too. In the soft state, HLX-1's emission is steadier, more thermal, and less variable. In the hard state, variability increases, suggesting the presence of a hot corona or low-efficiency accretion flow. So why does this matter so much? Because spectral state transitions are one of the most diagnostic features of black hole accretion. They are not seen in neutron stars unless there's accretion involved. They are not typically found in other exotic sources, like magnet Rs or white dwarfs. The pattern of these transitions, especially the relationship between spectral hardness and luminosity, acts like a fingerprint for black holes. HLX-1's fingerprint matches that of known accreting black holes, only it does so at a much higher luminosity. This is critical because it rules out alternative explanations. One could argue that HLX-1 is simply a neutron star undergoing super-Eddington accretion, or a background active galactic nucleus, AGN. But AGNs don't exhibit regular state transitions on year-long timescales. And neutron stars, especially ones that emit at HLX-1's level, would likely show thermonuclear bursts, pulsations, or other features that are notably absent here. The presence of these spectral states, and their cyclic recurrence, builds a case too strong to ignore. HLX-1 is behaving exactly like a black hole should. It also helps constrain the black hole's mass. The temperature of the soft-state disk emission in HLX-1 is significantly lower than in stellar mass black holes, as expected for a more massive accretor. In the standard disk model, disk temperature scales with black hole mass as roughly. For HLX-1, the disk temperatures during soft states are around 0.2 keV, much cooler than the 1 keV typical of a 10 solar mass black hole. This cooler temperature, combined with the high luminosity, again supports the intermediate mass hypothesis, placing HLX-1's mass firmly in the few thousand to 10,000 solar mass range. Additionally, these state changes offer clues about the accretion disk structure and the nature of the mass transfer. For HLX-1 to undergo repeated transitions, the companion star must supply a sufficiently large amount of matter during each periastron passage. That material then builds up in the disk, triggering a thermal instability that causes it to rapidly accrete, initiating the transition to the high/soft state. As the disk is depleted or stabilizes, the system cools and drops back into the low/hard regime. This kind of behavior isn't just consistent with black hole binaries, it's one of the defining traits of them. It tells us HLX-1 is operating under the same physical rules, despite its larger scale and extragalactic location. And that's incredibly powerful. It means the accretion processes we've studied in our own Milky Way hold true across the cosmos, even for black holes we once thought were only theoretical. Finally, HLX-1's state changes provide us with a way to test and refine our models of intermediate mass black hole accretion. Stellar mass black holes are plentiful, and supermassive ones have their own characteristics. But IMHs exist in a murky middle ground. By studying how HLX-1 flips between states, we can understand how accretion efficiency, disk instabilities, and magnetic fields scale with mass. This helps bridge the gap between small and large black holes, building a continuous narrative of black hole behavior across all mass ranges. In the end, HLX-1's ability to mimic the spectral state changes of known stellar mass black holes doesn't just make it interesting, it makes it essential. It's a cosmic echo of processes we already understand, amplified and stretched across light years. And it gives us one more reason to believe that we are finally witnessing what we've long been searching for, a real, functioning, intermediate mass black hole in action. In contemplating the true nature of HLX-1, there is a compelling speculation that takes shape, a question that stretches across cosmic scales and redefines our understanding of black hole behavior. Could HLX-1 be a miniature quasar? At first glance, that might seem like an exaggeration. Quasars, after all, are among the most powerful and luminous phenomena in the universe. Powered by supermassive black holes at the centers of distant galaxies, they shine with the brilliance of a trillion suns, often outshining their entire host galaxies. But fundamentally, the physics of a quasar is simple. It's a black hole consuming material at a high rate, generating intense electromagnetic radiation, especially in the ultraviolet and X-ray ranges, as matter heats up in the accretion disk and spirals inward. So if HLX-1 behaves in a similar way, but on a smaller mass and energy scale, then the quasar analogy may not be so far-fetched after all. Let's break it down. A quasar is typically defined not just by luminosity, but by the mode of accretion. In a quasar, the accretion rate is close to or even above the Eddington limit, meaning the black hole is consuming matter at the fastest rate possible before radiation pressure starts pushing material away. HLX-1 is known to radiate at luminosities exceeding ergs per second during its peak outbursts. That's more than 100 times the Eddington limit for a stellar mass black hole. This kind of luminosity, coupled with HLX-1's estimated mass of around 10,000 solar masses, places it squarely in the regime of Eddington-limited accretion, just like quasars. Furthermore, HLX-1's outburst cycles, driven by periodic accretion of material from a companion star, echo the variability seen in some active galactic nuclei. While most quasars are relatively steady emitters over human timescales, many show longer-term fluctuations, hinting at changes in the accretion rate, disk instabilities, or interactions with surrounding structures. HLX-1 compresses this variability into much shorter timescales, weeks to months rather than centuries. It gives us, in a sense, a fast-forward version of quasar-like behavior, one we can observe evolving in real time. In both HLX-1 and quasars, the accretion disk structure appears to be similar. HLX-1 exhibits a standard thin disk during its soft states, as inferred from its X-ray spectrum, a model also applied to quasar disks, albeit at much larger scales. The disk radiates thermally, peaking in X-rays for HLX-1 and in optical/UV for quasars, consistent with the difference in black hole mass. Remember, the temperature of the accretion disk decreases with increasing black hole mass, shifting the emission to longer wavelengths. That's why HLX-1 shines in X-rays, while a billion solar mass quasar glows in the optical. Yet both share the same physical mechanism, matter spiraling into a gravity well, radiating away energy as it descends. One might ask, do quasars always launch jets? In many cases, yes, and that's where HLX-1 presents an intriguing difference. Unlike the powerful radio jets seen in many quasars, HLX-1 appears to be either radio-quiet or completely lacking in jet activity. This doesn't disqualify the analogy, though. There are entire classes of radio-quiet quasars, where jet formation is suppressed or absent. The presence or absence of jets may depend on spin, magnetic field configurations, or accretion state. If HLX-1 lacks a strong magnetic field or isn't spinning rapidly enough to launch a jet, that could explain the radio silence. Alternatively, the brief flare episodes of HLX-1 might not last long enough for stable jets to form. Interestingly, there has been some radio emission detected near HLX-1, though it's very faint and only visible during certain outburst phases. This could be the fleeting remnant of a weak jet, or perhaps shock interactions in the accretion disk corona. It's not enough to match the large-scale jets of quasars, but it hints at a scaled-down version of the same physics. Another piece of the quasar analogy lies in feedback mechanisms. In quasars, radiation and jets can regulate star formation in the host galaxy, heat up surrounding gas, and shape the evolution of entire galactic cores. HLX-1 may not have the same reach, but its surrounding star cluster does show signs of disruption and possible heating. The intense radiation from HLX-1 could be impacting its local environment, stirring gas, perhaps even triggering or quenching star formation nearby. It's a small-scale echo of the grand quasar feedback process, once again pointing to HLX-1 as a miniature version of something much larger. Now here's where the idea becomes truly exciting. If HLX-1 is indeed a scaled-down quasar, it may offer a unique laboratory for studying accretion physics and feedback mechanisms without the complications of extreme distances, billion-year timescales, and the overwhelming brightness of galactic cores. HLX-1 is relatively close, only about 290 million light-years away. In cosmological terms, that's our neighborhood. And because it undergoes outbursts on manageable timescales, we can actually watch it change, evolve, and flare in real time. That makes HLX-1 something unique in the cosmic zoo, a transitional object. Too massive to be a typical X-ray binary, too small to be a full-scale AGN. It's a bridge, a stepping stone between classes, and a confirmation that the black hole accretion engine scales smoothly across orders of magnitude. The processes that power quasars a billion times more luminous than the Sun are the same ones driving HLX-1, just in miniature. In fact, some scientists have proposed that IMHs like HLX-1 may be the missing link in black hole evolution, the kind of object that helped fuel the first quasars in the early universe. If supermassive black holes were seeded by IMHs, then objects like HLX-1 aren't just analogues to quasars, they're ancestors of them. They may represent what quasars looked like in their infancy, before they devoured galaxies and became cosmic beacons. So yes, in almost every meaningful way, structure, behavior, luminosity-scaled physics, HLX-1 really does behave like a miniature quasar. And that insight is revolutionary. It reshapes our view of black holes, not as neatly divided into categories, but as continuously evolving entities whose behavior is governed by universal rules. HLX-1 may not light up the cosmos like a distant quasar, but in its compact fury and flickering brilliance, it gives us a precious glimpse into the same cosmic dance, one that started billions of years ago and continues, even now, just beyond our galaxy. When we consider the rarity of intermediate-mass black holes like HLX-1, we are staring into one of astronomy's deepest enigmas, not just about where such black holes are, but whether they ever existed in large numbers to begin with. Unlike their stellar mass and supermassive cousins, which form and behave in ways we can model with relative confidence, intermediate-mass black holes, or IMHs, occupy a strange and elusive middle ground. Their rarity isn't just about how difficult they are to detect. It's about how difficult they may be to even form. The story begins with the known ends of the black hole mass spectrum. On one side, we have stellar mass black holes, remnants of massive stars collapsing under their own gravity at the end of their lives. These are fairly common and observable, especially in binary systems or as X-ray sources. On the other end of the scale, we have supermassive black holes, behemoths of millions or even billions of solar masses, lurking at the centers of galaxies and powering quasars and active galactic nuclei. But what about the in-between? In theory, black holes with masses between roughly 100 and 100,000 solar masses should exist. These are what we classify as intermediate mass black holes. Yet, we've only found a handful of candidates, and many of those, like HLX-1, still await definitive confirmation. Why? Because IMHs are elusive by nature, and every mechanism we understand for creating black holes seems to skip over this mass range. Let's take a look at formation first. The death of a massive star, the typical route for forming a black hole, can only produce stellar mass black holes up to around 50 to 80 solar masses. Supernovae of larger stars tend to result in either total disruption or direct collapse, but still don't get you to the 1000 solar mass range or beyond. So if stellar deaths can't produce IMHs, how do they form? One hypothesis is hierarchical merging, the idea that many small black holes could merge inside dense star clusters, gradually building up to intermediate masses. But here lies the problem. Merging black holes tends to give off powerful gravitational waves that also carry away momentum. As a result, the newly formed black hole can be kicked out of the cluster due to recoil velocity, stopping further growth. It becomes a game of cosmic Jenga, where every success increases the instability of the stack. Another possibility is direct collapse of massive gas clouds, especially in the early universe before the first stars formed. These clouds could theoretically collapse under their own gravity into IMHs without fragmenting into stars. But such events would have been rare and happened billions of years ago. Any IMHs born this way would now be ancient, and unless they ended up in a galaxy's core, they'd be very hard to find. That leads us to the detection challenge. IMHs don't necessarily emit light unless they are actively accreting material. And even when they do, the luminosity might not be enough to distinguish them easily from other objects. A stellar mass black hole feeding slowly can look like a weak X-ray source, and a small IMH feeding rapidly might mimic a more energetic stellar system. Without clear, unique signatures, these objects get lost in the observational noise. Most of our current techniques for finding black holes involve watching gravitational interactions, how stars orbit an unseen mass, or how X-rays fluctuate during accretion events. But IMHs, especially those wandering between stars or floating through galactic halos, don't have easy-to-see gravitational effects. They're like cosmic ghosts, only detectable when they interact with something else. And even if an IMH ends up at the center of a dense star cluster, that still doesn't guarantee detection. The stellar velocities around it would have to be measured with extreme precision to infer the presence of a black hole. Even then, massive star clusters without black holes can sometimes produce similar dynamics. The boundary between a black hole-dominated core and a densely packed stellar population can be frustratingly ambiguous. In fact, many of the candidates for IMHs come from globular clusters, ancient, spherical collections of stars orbiting galaxies. These clusters have long been suspected of harboring IMHs at their centers, but observations remain inconclusive. The best claims, like those involving the clusters Omega Centauri or G1 and Andromeda, have been challenged, revised, or rejected due to new data or reinterpretation. This brings us to another important issue: mass estimation. Black hole masses are notoriously difficult to determine without a direct measurement method. For active accreting black holes, X-ray spectra and luminosity can give estimates, but they rely on models of disk behavior and accretion efficiency. Small changes in assumptions can swing mass estimates wildly. And for dormant black holes, only gravitational effects can tell the tale. But again, those effects may be subtle or easily misinterpreted. HLX-1 stood out because it was so luminous, so periodic in its behavior, and so convincingly distant. Its X-ray output simply couldn't be explained by a stellar mass black hole. But most potential IMHs are not so cooperative. They're quiet, faint, or too far away. Without steady feeding or violent mergers, they just drift invisibly through the dark. Gravitational wave astronomy, thanks to observatories like LIGO and Virgo, has begun to offer some hope. Some black hole mergers detected by LIGO involve black holes that fall into the so-called mass gap, objects too big to be stellar, but too small to be supermassive. These detections may be the first hints of an IMBH population we've long suspected but never observed directly. But even there, the mass estimates often hover near the edge of what's considered intermediate, and the interpretation is still debated. So, IMBHs remain rare not necessarily because they are few in number, but because they're hard to catch in the act. We might be surrounded by them, floating in galaxy halos, orbiting unseen through star clusters, or lying dormant in gas clouds. But unless they light up or shake the universe with gravitational waves, they remain invisible to our current instruments. That's why HLX-1 is such a profound discovery. It's a beacon, a flaring torch that says, "I'm here." And it confirms that such black holes can exist outside the stellar and supermassive regimes. It gives weight to theories, evidence to speculation, and direction to future searches. HLX-1 might not be alone, it might be the first of many, but until we find more, it will remain a cosmic rarity, a precious clue in an otherwise quiet realm of space. Understanding cosmic evolution, how the universe went from a nearly uniform sea of particles after the Big Bang to the structured, dynamic web of galaxies, stars, and black holes we observe today, requires solving a long-standing astrophysical mystery. How do supermassive black holes, which anchor nearly every galaxy, form and grow? HLX-1, in this context, is not merely a strange object lighting up the outer edges of a distant galaxy. It's a potential missing link in the story of black hole evolution, a bridge between the smallest and largest known forms of collapsed matter. To grasp the cosmic significance of HLX-1, we have to start by looking at the two well-established ends of the black hole mass spectrum. On one side are stellar mass black holes, typically formed from the remnants of massive stars after supernova explosions. These range from a few to perhaps a few dozen times the mass of the Sun. On the other side are supermassive black holes, gargantuan entities with masses of millions or even billions of solar masses, usually found at the centers of galaxies. The universe has plenty of both. What's missing is the evolutionary path that could connect the two. Supermassive black holes appear to have been in place very early in the universe's history. Some have been detected less than a billion years after the Big Bang. But that presents a serious problem. Stellar mass black holes grow slowly, even if they're feeding efficiently, and it shouldn't be possible for them to reach such enormous sizes in such a short span of time, unless there's an intermediate stage that allows rapid growth under special conditions. That's where intermediate mass black holes, IMBHs, like HLX-1, come into the picture. HLX-1 provides a real, observable example of what a growing black hole in this intermediate mass range might look like. Its estimated mass of around 10,000 solar masses places it comfortably in the territory required to seed supermassive black holes. It doesn't just suggest that IMBHs can exist, it shows how they might behave, what environments they might occupy, and what observational signatures they leave behind. Its periodic flaring, its intense X-ray luminosity, and its complex interaction with a likely companion star all demonstrate a dynamic system that could, over time, feed and grow. But HLX-1 does more than just prove that an IMBH can exist, it hints at how such objects may form and evolve. Its location in the outskirts of galaxy ESO 243-49 is not incidental. It's consistent with the theoretical scenario in which HLX-1 was once the central black hole of a dwarf galaxy that was cannibalized by ESO 243-49. During this process, the stars and gas of the smaller galaxy would have been stripped away, leaving behind its dense central region, including the black hole. This idea offers a compelling model of hierarchical growth, in which small galaxies, and their central black holes, merge over time to form larger systems. This hierarchical model is a key concept in understanding how structure forms in the universe. Galaxies merge, grow, and evolve over billions of years, and if black holes grow alongside them, then finding IMBHs like HLX-1 in such post-merger environments strengthens this theory. In other words, HLX-1 is not just a relic of cosmic evolution, it's an active participant in it. Furthermore, HLX-1's existence supports the notion that not all black holes evolve in galactic cores. If intermediate mass black holes can persist in satellite systems, globular clusters, or the outer halos of galaxies, then the map of where we should be looking for them suddenly becomes much broader. These black holes might be hidden in plain sight, faintly glowing or entirely dormant, in regions of the universe that are less densely studied. HLX-1 tells us to look beyond galaxy centers, to the edges, the outskirts, and the remnants of past mergers. On a larger scale, HLX-1 also provides an empirical checkpoint for simulations of galaxy and black hole coevolution. In cosmological models, the growth of black holes is tied to star formation, galactic mergers, and the inflow of cold gas. HLX-1, with its apparent link to a surrounding young star cluster, supports this narrative. The collocation of recent star formation and black hole activity suggests a shared history of accretion and environmental conditions that may mirror what happened in the early universe, when galaxies and black holes were forming rapidly and chaotically. Moreover, HLX-1 helps constrain the timing of black hole growth. By observing its current feeding rate, variability, and spectral state transitions, astronomers can reverse engineer possible growth paths. If HLX-1 continues accreting mass from its companion star in its current state, it could double in size over cosmic timescales. If such IMHs were common in the early universe and subjected to denser, richer environments, they could have grown even faster, reaching supermassive status by the time quasars first lit up the skies. From this perspective, HLX-1 becomes more than just a curiosity. It becomes a template, a reference object for what growing black holes might have looked like billions of years ago. It's a live-action example of processes that shaped the early universe, still playing out today in a quiet corner of another galaxy. It helps us decode the mechanics of growth, the importance of mergers, and the environments that foster the development of cosmic giants. In essence, HLX-1 is a fossil that breathes. It's a bridge between theories and observations, between stellar remnants and supermassive anchors, between a universe we can see and one we are only beginning to understand. By studying HLX-1, astronomers aren't just solving a mystery about one black hole, they are piecing together the architecture of the cosmos itself. Every detail adds to a growing framework of understanding, one that suggests the story of black holes is not written in extremes, but in a continuum, one where intermediate players like HLX-1 play a vital and long overlooked role. The nature of HLX-1 becomes even more compelling when one considers the idea that it might not have always belonged to its current galactic host. One of the leading theories about HLX-1's origin suggests that it may be the leftover core of a dwarf galaxy, a much smaller galaxy that was gradually consumed and assimilated by the much larger ESO 243-49. This isn't just poetic imagery, it's a scientifically grounded theory, and one that's not just plausible but likely when we consider how galaxies evolve over cosmic time. Galaxies grow by merging with other galaxies. This process, known as hierarchical assembly, is a cornerstone of modern cosmology. The universe began with small-scale structures, gas clouds and proto-galaxies, which over time merged into larger and larger systems, eventually forming the vast spiral and elliptical galaxies we see today. In the process of these mergers, the smaller galaxies often lose much of their mass and structure. Their stars are scattered, their gas is absorbed, and their overall identities fade into the gravitational landscape of their larger companions. But the central core of these dwarf galaxies can sometimes survive. At the heart of many dwarf galaxies lies a dense region, often a globular cluster or a compact nucleus, that is tightly bound by gravity. If the dwarf galaxy had its own black hole, this black hole would reside in that central region, nestled among stars too tightly packed to be easily stripped away. As the larger galaxy consumes the dwarf, this compact nucleus can survive the tidal chaos of the merger, orbiting around the host galaxy like a fossil remnant of its former self. That's where HLX-1 may come in. When astronomers first began to study HLX-1's location more closely, they noticed something peculiar. HLX-1 doesn't sit neatly in the disk or core of ESO 243-49. Instead, it appears offset from the main galaxy, residing in its outer halo, a remote and less dense region far from the galactic center. That's unusual. Stellar mass black holes are generally found within star clusters or stellar fields in the galactic disk, and supermassive black holes are always found at galactic centers. HLX-1, in contrast, hangs in space like a stray ember, too massive to be a typical stellar remnant, and too far from the core to be a supermassive black hole. This unusual placement supports the idea that HLX-1 may not have formed in ISO 243-49 at all. Instead, it might be the central black hole of a now disrupted dwarf galaxy, captured during a galactic merger. The telltale evidence for this lies not just in HLX-1's position, but in its stellar environment. Observations have revealed a cluster of young, blue stars surrounding HLX-1, stars that seem unusually concentrated and isolated compared to the rest of the galaxy. This stellar cluster resembles a nuclear star cluster, a dense group of stars that often surrounds the central black hole in smaller galaxies. If this interpretation is correct, what we're seeing in HLX-1 is not just a black hole, it's the decapitated head of a smaller galaxy that once roamed freely through space before being cannibalized by ISO 243-49. There are several reasons this theory carries weight. First, it explains how HLX-1 could become so massive in the first place. Dwarf galaxies, though small, can nurture intermediate mass black holes at their centers through periods of sustained star formation and accretion. If HLX-1 is one such example, then it represents the natural end state of black hole growth in a low-mass galactic environment. Second, this theory helps resolve the question of why HLX-1 is so bright. The black hole is currently feeding, likely on a donor star from its remnant cluster. This feeding activity could have been triggered by the gravitational turbulence caused during the merger. When the host dwarf galaxy was torn apart, some of its stars may have been thrown into new orbits, some falling inward toward the black hole and becoming sources of fuel. The intense gravitational stress could have compressed gas and triggered a phase of star formation, giving rise to the young stars we now see. Moreover, the merger scenario helps explain why HLX-1 appears alone in the outskirts of ISO 243-49. If the black hole had formed independently within the galaxy's disk, we would expect it to be part of a larger stellar structure. But HLX-1's isolation fits better with the idea of a stripped nucleus, no longer part of its original host, but still moving under the gravitational pull of the galaxy that devoured it. It also hints at a possible future trajectory. Over the course of billions of years, HLX-1 and its star cluster may spiral slowly inward toward the center of ISO 243-49, pulled by dynamical friction, a process where gravitational interactions with surrounding matter cause it to lose energy and fall closer to the galactic core. If that happens, HLX-1 could eventually merge with the central black hole of ISO 243-49, if it has one, contributing to the growth of a supermassive black hole. In that case, HLX-1 would go from being an interloping outsider to a building block in the cosmic engine room of a galaxy. This theory also carries exciting implications for the study of black holes across the universe. If HLX-1 is a relic of a swallowed dwarf galaxy, then there may be many more IMHs hiding in the halos of other galaxies, remnants of past mergers that have gone unnoticed because of their faintness or isolation. Galaxies like the Milky Way, which have undergone numerous mergers in their past, may host similar hidden black holes, lying dormant in the outer reaches of their halos or disguised within star clusters. HLX-1, then, becomes a kind of Rosetta Stone for galactic archaeology. By studying its location, its environment, and its behavior, we're learning not just about one object, but about the history of an entire class of black holes and the galaxies that once hosted them. We're uncovering the violent past of galactic cannibalism and tracing the evolutionary paths of black holes as they travel from small beginnings to cosmic significance. In that way, HLX-1 isn't just an astronomical anomaly, it's a living fossil from an ancient collision, drifting through space with the secrets of a galaxy that no longer exists. The story of HLX-1 becomes even more intriguing when we turn our attention to its stellar neighborhood, a compact gathering of young, luminous stars that seem to orbit the black hole like loyal companions. This group, while small and faint in the vast expanse of space, may hold the key to understanding HLX-1's origin, evolution, and even its current behavior. Often referred to as a young stellar cluster, this tight knot of stars isn't just a background feature, It might be a direct consequence of HLX-1's tumultuous history. At first glance, a black hole and a cluster of young stars might seem like an odd pairing. After all, black holes are often associated with destruction, while star formation is a symbol of creation. But the relationship between HLX-1 and its neighboring star cluster could be more than coincidental. It could be symbiotic, even causal. Observations from instruments like the Hubble Space Telescope have revealed that HLX-1 appears embedded within or adjacent to a dense grouping of hot, blue stars, stars that are estimated to be less than 200 million years old. That's incredibly young on cosmic timescales. This stellar cluster immediately drew the attention of astronomers because it's so unusual to find one like this in the outer halo of a galaxy, far from typical star-forming regions. Unlike galactic disks, which are rich in gas and dust that fuel star birth, halos are generally barren and cold. Yet here was a pocket of new life, shining brightly around a suspected intermediate mass black hole. That unusual location hinted that the stars and the black hole were not formed there, but had instead arrived together. So, how could a stellar cluster have formed around HLX-1 in such an unlikely region? One compelling explanation ties back to the idea that HLX-1 is the stripped nucleus of a dwarf galaxy. In this scenario, as the dwarf galaxy was captured and torn apart by ESO 243-49, tidal forces compressed the gas in its central regions, triggering a burst of star formation. The result? A new generation of stars formed around the already present black hole, creating a cluster that is now gravitationally bound to it. These stars, having formed from the remnants of the dwarf galaxy's interstellar medium, would naturally remain close to the black hole, orbiting it much like stars orbit the cores of more massive systems. Another possibility is that the cluster predates HLX-1's arrival in ESO 243-49's halo. It may have been part of the original dwarf galaxy, surviving the galactic merger intact. If so, the cluster's current youth might not reflect recent star formation, but rather a unique star formation history. Perhaps the dwarf galaxy experienced a late-stage starburst just before it was devoured. Either way, the presence of the cluster offers a rare opportunity to study the environment of an intermediate mass black hole in exquisite detail. The existence of this stellar cluster provides more than just circumstantial evidence of HLX-1's galactic past. It also affects how the black hole behaves today. As the black hole orbits within this cluster, it can occasionally capture material from nearby stars or disrupt them gravitationally. In fact, the accretion flares observed from HLX-1 may not solely result from a binary companion, but could also be supplemented by interactions with stars in the surrounding cluster. A dense cluster gives HLX-1 a rich environment from which to draw fuel, allowing it to exhibit the X-ray outbursts that have made it such a compelling target. Moreover, the dynamics of the cluster may help explain HLX-1's orbital stability. Unlike stellar mass black holes, which can be ejected from star clusters due to gravitational interactions, HLX-1's greater mass acts as an anchor. It dominates the gravitational potential of the cluster, helping to hold it together while it continues to feed and shine. The stars in turn provide a natural laboratory for testing gravitational theories, as their motions can, in principle, be tracked to map out the mass and influence of the black hole itself. The properties of the cluster, its mass, composition, and spatial distribution, also give us indirect ways of estimating the age of HLX-1's current state. If the cluster is young, that suggests the black hole only recently began its active phase, perhaps triggered by the merger with ESO 243-49. If the cluster is older, then HLX-1 may have been quietly lurking for a much longer time, only now showing signs of renewed activity. What's even more compelling is that similar black hole cluster associations have been suggested in other contexts, such as ultra-compact dwarf galaxies and massive globular clusters, where some astronomers suspect intermediate mass black holes might be hiding. HLX-1 and its stellar cluster may therefore serve as a prototype for these systems, a rare window into how black holes grow, migrate, and interact with their environments across cosmic epochs. If we had the capability to resolve the individual stars of this cluster with extreme precision, we might even be able to measure their orbits, using them like tracer particles to probe the gravitational well of HLX-1 itself. That's how the mass of the supermassive black hole at the center of the Milky Way was confirmed, by tracking stars like S2. Doing the same for HLX-1 would be more difficult due to its distance, but not impossible with future space telescopes like JWST, ELT, or LUVOIR. In the end, this cluster of young stars may be more than just a backdrop. It might be the smoking gun in HLX-1's story. Whether born from the ashes of a swallowed dwarf galaxy or the result of a post-merger starburst, it is a celestial neighborhood forged in upheaval and now glowing defiantly in the dark outskirts of a foreign galaxy. It surrounds one of the most mysterious black holes we've ever discovered, offering us clues not only about HLX-1's past, but about the very nature of black holes and their role in the cosmic tapestry. Understanding the true nature of HLX-1 requires looking at it through more than just one cosmic lens. Like piecing together a vast celestial jigsaw puzzle, astronomers have studied HLX-1 across multiple wavelengths, from high-energy X-rays to the subtle hues of optical light, and even into the ultraviolet spectrum. Each wavelength reveals a different aspect of the black hole's behavior and surroundings, offering critical insights that no single band of observation could provide on its own. This multi-wavelength approach has become essential in unraveling the mystery of HLX-1, helping to confirm that this enigmatic object is more than just a bright spot in the X-ray sky. The first and most obvious clue to HLX-1's presence was its extreme X-ray brightness. Detected initially by the XMM Newton Space Observatory in 2004 and confirmed in 2009 as a unique and persistent source, HLX-1's powerful X-ray emissions stood out immediately. With a luminosity exceeding 10 to the power of 42 erg/s, it outshone typical X-ray binaries by a factor of hundreds, or even thousands. These X-rays are believed to come from material being heated to millions of degrees as it spirals into the black hole, a process called accretion. The brightness and variability of these emissions strongly suggests the presence of a compact object, most likely a black hole, consuming material at an extraordinary rate. X-ray observations alone, however, can't provide the full story. They are essential for detecting accretion activity and flare cycles, but they don't reveal much about the larger environment around HLX-1, nor about its origins. That's where ultraviolet, UV, and optical observations come into play. These wavelengths allow astronomers to look beyond the immediate vicinity of the black hole, to the surrounding stellar cluster, to potential companion stars, and to the broader galactic context in which HLX-1 exists. Using the Hubble Space Telescope, HST, astronomers captured deep optical and UV images of the area around HLX-1. What they found was striking, a faint but compact optical counterpart precisely aligned with the X-ray source. This optical emission is not just the glow of the galaxy's background light, it appears spatially associated with HLX-1, possibly indicating either the stellar cluster around the black hole or accretion disk light being reprocessed into lower energy radiation. In the UV band, HLX-1 exhibits a modest level of brightness, consistent with either hot young stars or energetic processes in the accretion disk itself. This supports the idea that HLX-1 is not just an isolated X-ray source but part of a broader, dynamic system. The UV emission could be coming from the outer layers of the accretion disk, or it might even hint at the interaction between the black hole and a donor star, whose material is being stripped and funneled toward the black hole. Some interpretations suggest that this emission is consistent with ongoing or recent star formation, lending further weight to the hypothesis that HLX-1 is surrounded by a relatively young stellar cluster formed in the aftermath of a dwarf galaxy merger. Further optical observations, especially those that measure variability over time, have shown that HLX-1's brightness fluctuates not only in X-rays but also in optical and UV wavelengths. These variations are likely connected, as the black hole goes through its periodic flare cycles, brightening dramatically in X-rays every 400 days. Corresponding changes can sometimes be detected in lower energy bands. This synchronous behavior reinforces the idea of a multi-wavelength echo, where changes in one band are tied to dynamic processes in the accretion disk or the surrounding material. Additionally, spectroscopy in the optical band has provided indirect evidence of the composition and motion of the material near HLX-1. Though challenging due to its distance and faintness, Some spectroscopic measurements suggest the presence of helium and hydrogen emission lines, possibly linked to a surrounding gas cloud or even a donor star losing mass. These spectral features, while subtle, offer a tantalizing glimpse into the physical conditions near the black hole: temperatures, densities, velocities, all of which help refine models of HLX-1's mass and feeding behavior. Ground-based telescopes such as the Very Large Telescope, VLT, and Gemini Observatory have also played a key role. These observatories have used advanced adaptive optics and long exposure times to capture additional optical data. By combining the high spatial resolution of Hubble with the spectral resolution of these ground-based instruments, astronomers are able to disentangle the light of HLX-1 from the nearby galaxy ESO 243-49. That's no small feat. HLX-1 lies in the halo of this galaxy, where background contamination from starlight is significant. But with the right techniques, researchers have managed to isolate the black hole's signal and track its changes over time. Notably absent, however, are strong radio emissions, which would typically accompany relativistic jets seen in many other black hole systems, especially quasars and stellar mass black holes in certain accretion states. HLX-1 has shown some weak radioactivity, particularly during transitions between high and low X-ray states, but nothing as dramatic or sustained as seen in other systems. This radio faintness could mean that HLX-1 either lacks powerful jets or that they are too faint or misaligned to detect clearly. It raises fascinating questions about how jet formation scales with black hole mass, and whether HLX-1 represents a class of IMHs that accrete without launching prominent jets. The absence of strong radio emissions also sets HLX-1 apart from typical microquasars, stellar mass black holes in our own galaxy that exhibit powerful, jet-driven outbursts. It may suggest that the accretion environment around HLX-1 is jet-quiet, or that the mechanisms which produce relativistic jets in stellar mass and supermassive black holes don't operate the same way in intermediate mass ones. That in itself makes HLX-1 a vital testbed for studying how black holes interact with their surroundings at different mass scales. Crucially, all of this multi-wavelength data paints a picture of HLX-1 as a complex, multi-component system. It is not merely a point source of X-rays, but rather a dynamic and evolving structure that includes an accretion disk, a potential companion star, a surrounding star cluster, and interactions with the interstellar medium of its host galaxy. Each wavelength tells a different part of the story, and only by weaving them together can scientists approach a complete understanding. In the future, observations from next-generation telescopes such as the James Webb Space Telescope, JWST, the Nancy Grace Roman Space Telescope, and the Athena X-ray Observatory will likely refine our knowledge further. JWST, in particular, with its unmatched infrared sensitivity, could peer deeper into HLX-1's environment, revealing hidden stellar populations, cooler gas components, or dust clouds obscured in visible light. Athena's high-resolution X-ray spectroscopy might detect iron emission lines or other signatures that pin down the black hole's spin, feeding rate, or inclination. In this multi-wavelength symphony, HLX-1 continues to sing its strange, brilliant song. Each note, X-ray, UV, optical, and perhaps even infrared, adds a new dimension to our understanding. It is this diversity of observation that elevates HLX-1 from a mysterious light in the sky to one of the most important astrophysical laboratories in the known universe. While HLX-1 stuns with its intense X-ray luminosity and dynamic flaring behavior, there is one realm where it speaks only in whispers, if at all, the radio spectrum. For many black holes, particularly those that are accreting material, radio emissions serve as a kind of signature trail, evidence of powerful relativistic jets launching matter at near-light speeds into the interstellar medium. These jets, often observed in both stellar mass black holes and supermassive black holes and active galactic nuclei, light up the radio sky with their extended, energetic outflows. And yet, HLX-1 appears eerily silent in this domain. This lack, or extreme faintness, of radio emission has intrigued astronomers from the very beginning. If HLX-1 is truly a scaled-up version of a stellar mass black hole, or a scaled-down version of a quasar, it would be reasonable to expect jet formation, especially during transitions between accretion states. Such transitions are known to produce transient jet ejections in stellar mass black holes, and some have even been observed to mimic the entire jet cycle seen in supermassive black holes. But HLX-1 doesn't conform neatly to this pattern. A few attempts have been made to detect radio signals from HLX-1. Most notably, observations using the Australia Telescope Compact Array (ATCA) have managed to identify very faint radio signals, particularly during certain flare cycles when the black hole undergoes a transition from a low/hard to a high/soft X-ray state. This state switching is often associated with the ejection of material in jets, so detecting a faint radio counterpart during such a moment aligns with the standard model of accretion-driven jet activity. However, the emission is so marginal that it pushes the limits of detectability, and it doesn't persist consistently over time. The inferred radioluminosity is low, far lower than what one would expect for a black hole of HLX-1's estimated mass. If we assume HLX-1 truly has a mass of around 10,000 solar masses, then under conventional fundamental plane of black hole activity relations, correlating black hole mass, X-ray luminosity, and radio emission, its radio brightness should be significantly higher than observed. The fact that it isn't has forced scientists to rethink assumptions. Either the jet is inhibited, pointed away from us, short-lived, or HLX-1 simply doesn't produce one in the same way that other black holes do. This puzzling quietness raises fundamental questions about how jets are formed. Are jets solely the product of black hole mass and accretion rate, or do magnetic fields, black hole spin, and disk geometry play even more critical roles than we thought? HLX-1 might be missing one of these crucial ingredients, making it a radio-quiet IMH. Alternatively, its accretion flow might be fundamentally different, perhaps operating in a radiatively efficient regime that doesn't favor jet production. There's also the possibility that HLX-1's environment plays a role. Situated outside the main disk of ESO 243-49, HLX-1 may reside in a lower-density region of interstellar space, reducing the interaction between any potential jets and ambient matter. In a denser environment, even weak jets can produce noticeable radio emissions through synchrotron radiation, but in a sparse halo region, such emissions might go undetected. The jet might be present but hidden, cloaked by the very vacuum through which it moves. Another consideration is orientation. If HLX-1's jet axis is angled away from our line of sight, then the radio signals could be Doppler deboosted, making them far fainter than expected. This is a common challenge in black hole jet studies. The observed strength of a jet isn't just a matter of intrinsic power but of geometry. Even a moderately powered jet could appear vanishingly dim if viewed from the wrong angle. Without precise constraints on the inclination of HLX-1's system, this remains a plausible explanation. Interestingly, the lack of strong radio emission may also tell us something about black hole evolution. There is an emerging theory that black holes might cycle between radio-loud and radio-quiet states depending on their evolutionary phase or the structure of their accretion flow. HLX-1 might represent a radio-quiet phase in this cycle, or it may be on a long-term evolutionary path that favors thermal accretion without relativistic jet launching. The absence of prominent jets doesn't necessarily diminish HLX-1's importance. In fact, it may enhance it. This deviation from the norm challenges scientists to build more nuanced models of black hole accretion and energy output. Rather than being an outlier to be dismissed, HLX-1 could be a new archetype, showcasing how black holes of intermediate mass might evolve differently than their smaller or larger counterparts. And there's another layer of intrigue. If HLX-1 doesn't launch jets, it may be more representative of a quiescent population of IMHs that we have yet to detect. Most of the black holes we currently know about are either bright X-ray binaries or loud AGNs, precisely because they are easy to see. But the universe could be teeming with quiet, jetless IMHs, invisible to radio surveys and only discoverable during brief accretion flares. HLX-1 could be the tip of that hidden iceberg, offering a glimpse into a much larger, silent population. In the quest to understand the full spectrum of black hole behavior, HLX-1's radio silence is not a void, it's a signal in itself, one that tells us our frameworks are still incomplete. Why this black hole shines so brightly in X-rays while whispering in radio remains an open question, and one that may take decades, and next-generation telescopes, to fully resolve. Until then, HLX-1's quiet defiance of expectations continues to be one of its most mysterious and thought-provoking features. Despite the compelling body of evidence supporting HLX-1 as a prime candidate for an intermediate mass black hole, IMH, astronomers are still cautious to affix a definitive label. The core of the challenge lies not in what we can see, but in what we can't. Even with modern space telescopes and advanced analysis tools, definitively confirming the identity of an IMH remains among the most elusive tasks in astrophysics, and HLX-1 sits right at the center of this conundrum. To understand why, consider the nature of black holes themselves. These are entities that emit no light of their own. What we observe from HLX-1 is not the black hole directly, but the extreme behavior of its surroundings, primarily the radiation produced by material falling into it. This accretion process is a powerful source of X-rays, which is why HLX-1 was flagged as a hyperluminous X-ray source. But X-rays alone, no matter how intense or well-behaved they are, don't give us a mass reading stamped with certainty. In the case of HLX-1, mass estimates are derived indirectly. Researchers use its luminosity, its X-ray spectral states, and models of accretion physics to infer a mass of around 10,000 solar masses, placing it solidly in the IMH range. Yet this estimate depends heavily on assumptions about the efficiency of accretion, the orientation of the disk, and the distance to the object. A modest error in any of these variables can swing the mass estimate dramatically. What if HLX-1 is actually closer than we think? Or if its disk is seen at a more oblique angle? Or if its accretion flow is atypically efficient or inefficient? Each of these possibilities introduces ambiguity. Then there's the problem of dynamic measurement, the gold standard for determining black hole masses. With stellar mass black holes, astronomers often measure the orbital motion of a companion star, using Kepler's laws to calculate the mass of the unseen black hole tugging on it. In supermassive black holes, we observe the orbits of stars near galactic centers, such as the famous stars orbiting Sagittarius A, to determine the central mass. But with HLX-1, we're observing an object in another galaxy, ESO 243-49, located about 290 million light-years away. At such distance, we cannot resolve individual stars or directly observe orbital dynamics. No telescope can currently deliver that level of detail. So, we fall back on indirect methods, modeling how the accretion disk emits X-rays, comparing HLX-1's behavior to known black holes, looking for features like spectral state transitions or flare recurrence patterns. And while HLX-1 lines up astonishingly well with what we'd expect from an IMH, all of it is circumstantial. Imagine trying to deduce the size of a raging fire solely by how bright the smoke is from miles away. You'd get a strong hint, but not an exact answer. Another significant hurdle is the lack of similar candidates. IMHs are so rare, or so rarely detected, that we don't have a large enough population to establish firm empirical patterns. With only a few tentative IMHs discovered, and none confirmed beyond dispute, we lack the statistical confidence needed to generalize. HLX-1 might fit our best models of IMH behavior, but what if our models are wrong? Or what if HLX-1 is the exception rather than the rule? Additionally, instrumental limitations continue to bottleneck our investigations. X-ray observatories like XMM Newton and Chandra have revealed crucial insights, but they weren't designed to perform high-resolution mass measurements at extragalactic distances. More sensitive instruments, such as the upcoming Athena X-ray Observatory, may help refine our understanding, but for now, we remain constrained by the tools we have. There's also the challenge of multi-wavelength ambiguity. As discussed previously, HLX-1 is nearly silent in radio, and its optical and UV counterparts are faint and difficult to disentangle from the background light of ESO 243-49. This makes it difficult to study HLX-1's environment in detail, an important step in confirming its black hole status. If it were possible, for instance, to study its stellar neighborhood, We might find kinematic signatures of an orbiting companion star or evidence of past galactic mergers, both of which could strengthen the IMBH case. And finally, there's the philosophical hesitation in the scientific community. Black holes have historically forced paradigm shifts in our understanding of the universe, and scientists are naturally cautious about making bold claims without irrefutable proof. HLX-1 may look, behave, and shine like an intermediate mass black hole, but without a smoking gun like a gravitational wave detection or a dynamical mass measurement, its status will always carry an asterisk. This is the paradox of HLX-1. It is one of the strongest candidates we've ever found for an IMBH, yet it continues to be labeled a candidate, not a confirmation. Its light is bright, its patterns familiar, its behavior convincing, but science demands more than persuasion. It demands measurement, replication, and precision. Until our instruments are capable of penetrating the veil of distance and detecting the mass directly, HLX-1 will remain a cosmic riddle, immensely suggestive, but not fully solved. Still, it's a riddle we're determined to answer. Every new flare, every spectral shift, every faint photon it sends our way brings us a step closer to unlocking the truth. HLX-1 may not have given up all its secrets yet, but it continues to teach us where to look, how to think, and what questions still remain about the elusive middleweights of the black hole family. For all the dramatic evidence that surrounds HLX-1, its intense X-ray flares, its recurring outbursts, and its likely gravitational pull on a companion star, there remains one profound absence. We have never directly seen its event horizon. This isn't unique to HLX-1, of course. No black hole, by its very definition, emits light from within its event horizon. The very structure of a black hole ensures that once anything crosses this invisible boundary, not even photons, the fastest carriers of information, can escape. So how could we see what is, by its nature, unseeable? In the case of supermassive black holes like Sagittarius A or M87, the solution lies in indirect imaging. The Event Horizon Telescope, for instance, doesn't capture a black hole directly. It captures the silhouette, or shadow, cast by the event horizon against a glowing backdrop of infalling material. But this technique only works for black holes that are both large enough and close enough. M87 is 6.5 billion solar masses, and even then, imaging it required an Earth-size virtual telescope array. HLX-1, with a mass on the order of 10,000 solar masses, is far too small, and far too distant, being located around 290 million light-years away, for current technology to resolve anything like a silhouette. So we find ourselves relying again on inference. For HLX-1 to have an event horizon, it must exhibit behavior consistent with general relativity's predictions for black holes. And to be fair, it does. The way it flares, the way matter appears to vanish without a trace into it, the way radiation emerges only from outside a certain boundary, all of this mimics the signatures we associate with event horizons. Yet none of these phenomena can definitively prove an event horizon exists. There are exotic theoretical alternatives to black holes, like gravastars, boson stars, and even wormholes, that can mimic many black hole behaviors, at least from a distance. One of the most convincing indirect pieces of evidence for an event horizon is the absence of a hard surface. For example, if HLX-1 were a massive, dense object without an event horizon, say, a large neutron star-like body, it would theoretically possess a surface for material to crash into. That crash would produce a distinctive burst of electromagnetic radiation as infalling matter struck the object. But HLX-1 doesn't emit such surface impact signatures. Instead, it behaves as though infalling material simply disappears beyond a point of no return, consistent with what we expect from a true black hole. Yet again, the problem is not that HLX-1 is behaving incorrectly. It's that we can't rule out all the other things it might be. That's the scientific burden of proof, ruling out every alternative. And at distances like these, with no way to spatially resolve HLX-1's immediate surroundings, even the absence of a surface is based on interpretation, not measurement. This leaves just enough room for ambiguity that critics of the IMBH designation can still raise a skeptical eyebrow. Instruments that could potentially settle the issue, such as more sensitive X-ray timing telescopes or next-generation gravitational wave detectors, are still on the horizon themselves. The Athena X-ray Observatory, for example, might offer deeper insights into HLX-1's accretion disk structure, potentially identifying echoes or reverberations of X-ray light that could help us map how space behaves near its central object. These echoes could reveal whether the space around HLX-1 curves inward toward a featureless void, or whether there's something more complex, something solid, lurking just beneath our observational threshold. Another hope lies in the study of quasi-periodic oscillations (QPOs), rhythmic flickers in X-ray brightness that sometimes emerge near black holes. These oscillations are thought to originate from matter orbiting very close to the event horizon. If detected in HLX-1 and if they show certain frequency patterns, they might further constrain the object's mass, spin, and even the geometry of spacetime near it. But again, we are talking about inference layered upon inference. HLX-1 is a whisper in the dark of deep space, and we are trying to eavesdrop from across a cosmic ocean. There is also a tantalizing thought within the community. If HLX-1 were to undergo a dramatic event, a tidal disruption, for example, in which it shreds a star completely, the resulting light curve and emission spectrum might give us clearer signs of an event horizon. We'd be able to watch, in real time, as matter spirals inward and either vanishes or crashes into something tangible. But such events are unpredictable and rare. So, for now, the event horizon of HLX-1 remains a ghost, unseen, but not unimagined. Its effects ripple outward in the form of light and heat and motion, but its actual boundary remains hidden, tucked behind the curtain of modern technological limits. We are left with faith in physics, trust in the theory of general relativity, and an ever-growing hunger for observational evidence. To see an event horizon, one must do more than look. One must listen to the echoes of gravity, observe the dance of matter, and interpret the silence between bursts of light. HLX-1 offers us many signs, but the final proof remains just beyond reach, for now. Understanding HLX-1, an enigmatic celestial body located hundreds of millions of light-years from Earth, demands far more than just observing its flickering light from afar. Astronomers and astrophysicists rely heavily on simulations and theoretical modeling to peel back the layers of this black hole candidate and reconstruct a picture of what's really happening in that distant corner of the universe. Because we can't see black holes in the conventional sense, we turn to physics, mathematics, and computer modeling to replicate the forces and conditions at play. Modeling HLX-1 starts with first principles: gravity, thermodynamics, relativistic physics, and fluid dynamics. These are the universal laws that govern the behavior of all black holes, from the small to the colossal. In HLX-1's case, researchers input observational data, such as X-ray luminosity, variability patterns, spectral features, and timing signatures, into advanced simulations that recreate how matter behaves near a black hole of about 10,000 solar masses. One of the first tasks in these simulations is to simulate the accretion disk, the swirl of superheated gas spiraling into the black hole. In HLX-1, this disk flares with dramatic intensity roughly every 400 days. That alone gives modelers a key clue: the black hole is likely pulling material from a companion star, and the accretion happens in bursts. Simulations explore various orbital configurations and disk instabilities to match this periodic behavior, allowing researchers to test whether a binary system can reproduce the timing and intensity of HLX-1's X-ray flares. This brings us to hydrodynamic simulations. These model how gas flows under the influence of gravity, radiation pressure, and viscous forces. For HLX-1, scientists have used these simulations to estimate how much mass must be flowing into the black hole during outbursts. The results are often stunning. To match the X-ray brightness we see, HLX-1 would need to be accreting at a rate of several times that of typical stellar mass black holes, which fits the theory of a much larger, intermediate mass black hole. But hydrodynamics alone isn't enough. The relativistic effects near the event horizon of a black hole, where gravity warps time and space, require incorporating Einstein's equations into the models. General relativistic magnetohydrodynamic, GRMHD, simulations are among the most sophisticated tools in the astrophysical toolkit. They take into account not just the flow of gas, but the role of magnetic fields and relativistic effects on that flow. In the case of HLX-1, GRMHE models help refine our understanding of how angular momentum is transported within the accretion disk, how jets might, or might not, form, and what kinds of instabilities might trigger the periodic flare-ups. Another important component of these simulations is radiative transfer, the modeling of how radiation, particularly X-rays and ultraviolet light, travels through and emerges from the hot plasma surrounding the black hole. By comparing simulated light curves and spectra to those observed by instruments like XMM Newton, Chandra, and Swift, researchers can iterate on their models, tweaking physical parameters like the black hole's spin, inclination angle, and accretion rate to better fit the data. The strength of these simulations is their ability to test hypotheses that would otherwise remain unprovable due to our observational limitations. For example, to estimate HLX-1's mass, scientists simulate a wide range of black holes, from a few hundred to tens of thousands of solar masses, and evaluate which one best replicates the observed behavior. The models that consistently produce the correct X-ray luminosity, spectral states, and variability patterns tend to converge on a mass around 10,000 solar masses, placing HLX-1 squarely in the intermediate mass regime. Beyond the accretion disk and radiation, simulations are also used to explore the larger environment around HLX-1. Some models test how HLX-1 could be the remnant of a stripped dwarf galaxy merging into ESO 243-49. In these simulations, the gravitational dance between galaxies can pull smaller satellite galaxies apart, feeding their black holes into larger galactic systems. By modeling such interactions over billions of years, researchers can understand how HLX-1 might have ended up embedded in a star cluster on the outskirts of another galaxy, like a fossil of galactic cannibalism. Interestingly, the presence or absence of jets can also be explored via simulations. HLX-1 is mostly quiet in radio wavelengths, suggesting a lack of prominent jets. Jet formation is highly sensitive to the spin of the black hole and the geometry of the magnetic fields threading the accretion disk. Some models indicate that low-spin black holes, or those with weak magnetic alignment, might fail to launch significant jets, which could explain HLX-1's relative radio silence despite its energetic outbursts. Even the timing of HLX-1's flare cycles has been the subject of extensive modeling. By simulating a binary system where a donor star is on an eccentric orbit, researchers can match the roughly 400-day cycle as the point where the star swings closest to HLX-1 and dumps material into the disk. These models help determine the mass, orbit, and structure of the possible companion star without ever directly observing it. On top of all this, simulations also give us a window into potential future observations. As new telescopes like Athena or the Square Kilometre Array come online, simulations can predict what kinds of signals we should expect. If, for example, Athena's improved spectral resolution detects specific features in HLX-1's X-ray emissions, these can be used to further refine the black hole's spin, mass, and inclination. Some simulations are even built to project into future scenarios. What might happen if HLX-1 accretes at a higher rate? Could it transition into a more persistent luminous phase, or even trigger detectable gravitational waves through tidal disruption events? Thus, simulations are more than just digital playgrounds for theoretical physics. They are testbeds for reality. They allow scientists to recreate the cosmic laboratory of HLX-1, manipulate variables we can't directly measure, and refine our understanding with each new dataset. HLX-1 may be 290 million light-years away, but through the power of simulation, it is pulled into the minds and computers of researchers on Earth, modeled again and again until its secrets begin to yield to our curiosity. In the heart of HLX-1's mystery lies a powerful opportunity, one that doesn't just help us classify a black hole, but one that could push the boundaries of physics itself. HLX-1, by virtue of its mass, behavior, and activity, sits in a unique position to test theories of accretion physics and general relativity, two of the most important frameworks that describe how matter and energy behave under the extreme conditions created by massive compact objects. While much of our current understanding of these concepts has been developed through the study of stellar mass black holes and supermassive black holes, HLX-1 exists in that elusive in-between space, offering a rare and invaluable case study for verifying how these laws scale across vastly different regimes. One of the key aspects of general relativity that HLX-1 helps explore is the curvature of spacetime around a massive object. Einstein's theory predicts very specific behaviors for matter and light near a black hole, such as gravitational redshift, time dilation, and the warping of light paths. In HLX-1's case, we can't yet directly image the space around it, as has been done with the Event Horizon Telescope for M87 and Sagittarius A. But we can observe how material in the accretion disk behaves under the influence of its gravity, and that behavior carries within it the signatures of relativistic physics. For instance, the inner regions of the accretion disk around HLX-1 orbit at relativistic speeds, close to the speed of light. The way X-rays are emitted and Doppler shifted from this spinning disk provides insights into how spacetime is distorted by the black hole's gravity. Observing and analyzing these emissions allows scientists to compare the data with predictions from relativistic models, testing how well general relativity describes the environment around an object that's thousands of times the mass of the Sun but not quite as extreme as the million or billion solar mass giants at galactic centers. One fascinating phenomenon associated with relativistic disks is the broadening and skewing of iron emission lines, often seen in the X-ray spectra of black holes. These lines can become stretched and shifted due to the extreme gravitational field near the black hole's event horizon. While detecting such features in HLX-1 has proven challenging due to distance and signal limitations, their possible presence would give astrophysicists a direct probe into how matter interacts with curved spacetime on an intermediate scale, something rarely observable. Moreover, the timing of HLX-1's flare cycles, every 400 days or so, also provides a relativistic laboratory. Theory suggests that the companion star might be on a highly elliptical orbit, approaching HLX-1 at intervals and dumping mass into its accretion disk. The way this interaction happens, and the delay between periastron passage and flare peak, can be influenced by relativistic precession. Just like Mercury's orbit precesses due to the curvature of spacetime around the Sun, orbits in close proximity to black holes can undergo similar but far more dramatic shifts. These shifts, if detected in HLX-1's behavior, would offer direct confirmation of general relativity at intermediate black hole masses. Another arena where HLX-1 becomes a playground for relativistic physics is in the study of frame dragging, a prediction of general relativity where space itself is twisted by a rotating black hole. While we've inferred frame dragging effects around stellar mass black holes and hope to do so around supermassive ones, HLX-1 provides a middle ground. If its black hole is spinning, as most are believed to be, and if the inner accretion disk is misaligned with the spin axis, it could experience lens-stirring precession. This could cause the disk to wobble, modulating the light we observe in a quasi-periodic way. Identifying such patterns in HLX-1's light curves could offer a way to measure the spin of the black hole, a key property that reveals information about its formation and growth history. But HLX-1 is not just about general relativity. It also serves as a critical testbed for accretion physics. How matter spirals into a black hole, heats up, emits light, and sometimes even produces jets is one of the most important, and still mysterious processes in high-energy astrophysics. HLX-1's flaring behavior gives us a front-row seat to this drama. When it brightens dramatically in X-rays, it likely shifts between accretion states, similar to what we observe in stellar mass black hole binaries. In these states, the structure of the accretion disk changes, and different physical mechanisms dominate the energy output. These state transitions are thought to be governed by instabilities in the accretion disk, specifically, the thermoviscous instability, which can cause the disk to flip between a cool, faint state and a hot, bright one. Observing HLX-1's transitions helps confirm whether these same instabilities scale with mass, supporting the universality of accretion disk theory. If HLX-1 shows the same hysteresis loops in its hardness intensity diagrams that stellar mass black holes do, it would strengthen the idea that the same underlying physics governs accretion across all black hole sizes. Another major concept in accretion theory that HLX1 helps test is the role of Eddington luminosity, the point at which the outward pressure of radiation balances the inward pull of gravity. Theoretically, black holes can't accrete at rates significantly above this limit, but observations have found cases where they seem to do just that. HLX1 appears to operate near or at its Eddington limit during outbursts, which makes it an ideal subject for studying how black holes manage to feed so efficiently. Do they bend the rules by beaming their radiation, or by using slim disks where the radiation pressure is channeled differently? HLX1's behavior can help answer these questions. The absence of strong radio jets in HLX1 also poses interesting challenges and opportunities for accretion theory. Jets are often produced when black holes accrete in specific states, typically in the low/hard state, but HLX1 doesn't show the same jet signatures we might expect, even during transitions. This suggests that jet production may depend on other factors, such as black hole spin or magnetic field structure, and that intermediate mass black holes might differ in how they launch jets compared to their smaller or larger cousins. Lastly, HLX1 serves as a proving ground for emerging theories that attempt to unify accretion behavior across all scales. The fundamental plane of black hole activity is a proposed relationship that connects X-ray luminosity, radioluminosity, and black hole mass across the entire black hole mass spectrum. If HLX1 falls on this plane, and early studies suggest it might, it would provide compelling evidence that this relationship is truly universal. On the other hand, any deviation HLX1 shows could signal new physics at intermediate masses, forcing theorists to revise their models. In all these ways, HLX1 is far more than just a distant point of light. It's a cosmic crucible for theories both old and new. By pushing the limits of relativity and accretion theory into previously untested territory, this hyperluminous X-ray source opens the door to a more complete and unified understanding of how black holes work, from stellar corpses to galactic giants, and now, thanks to HLX1, the mysterious middleweights in between. If HLX1 represents a true intermediate mass black hole, then it doesn't just challenge existing black hole classification, it also reshapes how we might detect and study such objects in the future, especially through gravitational waves. Gravitational wave astronomy has exploded since the first detection in 2015 by LIGO, where two stellar mass black holes spiraled into one another and merged. That landmark event opened a new window on the universe, not one made of light, but of ripples in spacetime itself. And now, as we look at HLX1 and others like it, we begin to imagine a future where gravitational waves do for intermediate mass black holes what X-rays have done so far: reveal them, confirm them, and let us explore them in incredible detail. HLX1 is not currently producing detectable gravitational waves, at least not in a way that current observatories like LIGO or Virgo could perceive. Its outbursts and feeding events are dramatic in X-rays, but they don't generate the kind of cataclysmic mass motion, like a black hole merger, that would be necessary for strong gravitational wave emissions. Still, it's precisely its existence that helps pave the way for what could be found through gravitational waves in the future. The key lies in the possibility that HLX1, or others like it, may have formed through previous mergers, perhaps of smaller black holes or dense stellar clusters. And if such mergers are still occurring across the universe, then gravitational wave detectors are the perfect instruments to catch them in the act. For intermediate mass black holes to be detected via gravitational waves, we would need a binary system involving at least one IMH, perhaps two intermediate mass black holes merging, or an intermediate mass black hole merging with a stellar mass companion. These types of events would produce gravitational wave signatures that fall into a sort of observational sweet spot for next-generation observatories. LIGO and Virgo are already close to this threshold, but it is missions like the upcoming space-based observatory LISA, the Laser Interferometer Space Antenna, that hold the greatest promise. Unlike ground-based detectors that are limited by seismic and environmental noise, LISA will orbit in space and detect lower-frequency waves, perfect for capturing the slower, longer spirals of massive black hole mergers. And here's where HLX1 becomes especially important. If it truly is a black hole with a mass around 10,000 times that of the Sun, then it represents the lower boundary of LISA's most sensitive range. LISA will be tuned to detect gravitational waves from mergers involving black holes between 100 and 100,000 solar masses. Events involving IMHs are expected to be rare, but they should exist if objects like HLX-1 are not anomalies, but representatives of an underexplored population. The detection of such events would be groundbreaking. Not only would they confirm the existence of more IMHs, but the signals would carry precise information about the black hole's masses, spins, and the nature of spacetime in their vicinity. Even beyond LISA, other proposed instruments like the Einstein telescope or Cosmic Explorer could further enhance our ability to probe these elusive giants. These detectors will have improved sensitivity and may be able to detect IMH mergers at higher frequencies or from farther distances. In tandem, they could offer overlapping coverage, providing a multi-frequency, multi-scale view of the gravitational universe. But it's not just about detection, it's also about tracing cosmic history. Each gravitational wave signal from an IMH merger tells a story of formation. Did the black holes grow in isolation, slowly accreting mass? Or were they born in the chaotic cores of dense star clusters, colliding with each other like cosmic billiard balls? HLX-1's potential origin, possibly as the core of a stripped dwarf galaxy or from the merger of several stellar remnants, feeds directly into these questions. If we start detecting gravitational wave signals from IMHs forming in similar ways, we'll begin to map out the life paths of these hidden titans. There's another exciting possibility: intermediate mass ratio in spirals, or IMRIs. These involve a smaller stellar mass object, like a neutron star or black hole, spiraling into an intermediate mass black hole. These events produce distinctive gravitational wave signatures that are rich in information. Unlike rapid, high-frequency mergers, IMRIs produce long, slowly evolving signals, sometimes lasting weeks or even months in the LISA frequency band. These prolonged signals provide an exquisite test of general relativity, space-time curvature, and the black hole's properties. If HLX-1 has a compact object orbiting it, like the hypothetical companion star discussed earlier, then perhaps in millions of years, we'd observe such an in-spiral. But even now, there may be other HLX-1-like systems undergoing this very process, hidden across the cosmos, waiting for the right instruments to find them. We also have to consider population statistics. So far, HLX-1 is the best candidate we've found, but that doesn't mean it's unique. It could simply be the tip of the iceberg, the only one visible because of its advantageous location and viewing angle. If gravitational wave detections begin to turn up multiple IMH merger events, then we'll finally have a statistical handle on how many of these objects really exist, and what roles they play in the grand evolutionary arc of the universe. Did they seed supermassive black holes in the early cosmos? Do they lurk in the cores of globular clusters? Are they the hidden link that completes our picture of black hole evolution? In this context, HLX-1 stands as both a beacon and a challenge. Its discovery by electromagnetic means, primarily X-rays, has made it a prototype. But its true potential may only be unlocked when we start detecting its gravitational cousins, events that we can't see with light, but only hear with the vibrations they send across spacetime. In this way, HLX-1 has become a signpost pointing toward a richer, more multidimensional future in astrophysics. It tells us not just what is visible, but what might be hidden. Not just what burns bright, but what rumbles in silence. When the first intermediate mass black hole merger is detected, we will look back at HLX-1 as the harbinger, the first in a family of cosmic giants who, for so long, escaped detection. With gravitational wave astronomy poised to mature rapidly in the coming decades, the hunt is just beginning. And HLX-1, silent but luminous, watches from afar, waiting for the moment when the universe reveals others like it, not with photons, but with echoes in the fabric of existence itself. The journey to understand black holes has always been about bridging gaps. Gaps in size, gaps in formation theories, and gaps in observational data. For decades, astronomers believed in two distinct classes of black holes: the stellar mass black holes formed from the collapse of massive stars, typically weighing a few dozen solar masses, and the supermassive black holes anchoring the centers of galaxies, with masses ranging from millions to billions of suns. The existence of anything in between, intermediate mass black holes, was speculative at best. Yet as the search advanced and our instruments grew more sensitive, we began to see hints, tantalizing and ambiguous, that such objects might indeed exist. HLX-1 has emerged as one of the clearest signposts in this uncertain terrain, anchoring our understanding in something that is both detectable and profoundly mysterious. When we place HLX-1 into the broader picture of black hole research, we realize it may represent more than just an anomaly. It may be the missing piece in one of astrophysics' grandest puzzles: how black holes grow across cosmic time. We know that stellar mass black holes are common. We've found them in binary systems, seen them through their accretion of nearby matter, and detected their mergers via gravitational waves. We also know that nearly every large galaxy has a supermassive black hole at its center, including our own Milky Way. What we don't fully understand is how the universe got from the former to the latter. How did these monsters grow so enormous so quickly, especially when we observe quasars powered by billion solar mass black holes less than a billion years after the Big Bang? There are only a few possibilities that could explain such rapid growth. One is that supermassive black holes were seeded directly from massive gas clouds collapsing in the early universe, so-called direct collapse black holes. Another is that they grew from smaller black holes through accretion and mergers, gradually increasing in mass over cosmic timescales. This second possibility implies a population of intermediate mass black holes should exist, acting as transitional objects in this growth hierarchy. HLX-1, with its estimated mass of around 10,000 solar masses, sits perfectly within this expected, but largely unobserved, category. In that sense, HLX-1 isn't just important for what it is. It's important for what it represents, a class of objects that could explain how the universe built its most massive gravitational engines. If intermediate mass black holes like HLX-1 were common in the early universe, they could have merged with one another or with stellar mass black holes to form progressively larger structures, eventually reaching the scale of supermassive black holes. Their presence today, if we can find more of them, might even tell us how these ancient growth processes unfolded. And that brings us to an important realization: HLX-1 is not just a clue in isolation. It's a window into the universe's formative years. If HLX-1 was born from the core of a dwarf galaxy or from the collapse of a dense star cluster, then it carries within it the fossil record of those events. Studying it can tell us not just about the object itself, but about the environment that gave birth to it. This includes details about the metallicity of its surroundings, the types of stars that may have contributed to its formation, and the dynamics of its host galaxy, ESO 243-49. And in turn, that insight can be scaled and applied to other galaxies, both nearby and far away, where similar processes might have played out. Moreover, HLX-1's interactions with its environment, the surrounding star cluster, the potential donor star, the galactic halo, create a sort of astrophysical laboratory. These interactions, when measured across different wavelengths and observed over time, give us clues about how matter behaves near such an exotic object. The way HLX-1 accretes matter, the way it produces X-rays, the way it possibly feeds in cycles, these are all echoes of the larger processes that might have once governed the feeding of supermassive black holes and active galactic nuclei and quasars. If HLX-1 truly behaves like a miniature version of these behemoths, it means we can study high-energy phenomena on a smaller, more observable scale, almost like watching a simulation of cosmic evolution unfold in real time. There's also a feedback loop at play here between observation and theory. HLX-1 challenges models of black hole formation, prompting theorists to revisit assumptions and simulations. Why do we see so few IMHs, even though theories suggest there should be many? Are they being missed because they don't accrete much and are therefore faint? Are we looking in the wrong places, focusing on the centers of galaxies when they may exist in off-nucleus regions, like HLX-1 does? Or are they transient objects, created in rare conditions that don't last long in cosmic time? Every answer we pursue leads to new questions, and HLX-1, sitting serenely in another galaxy, seems to embody them all. Importantly, HLX-1 also symbolizes a shift in astronomical methodology. It underscores the importance of multi-wavelength astronomy. Its X-ray brightness first drew attention, but it's been studied in ultraviolet, optical, and radio wavelengths too, even though it is largely radio quiet. It shows us that only by combining data across the spectrum can we truly piece together the identity of such objects. That's how we confirmed its location in galaxy ESO 243-49, traced its outbursts, and estimated its mass. The broader effort to understand black hole evolution requires this kind of multi-layered investigation. It's no longer enough to observe a black hole in one part of the spectrum. We need to build a complete picture, and HLX-1 is a shining example of how that can be done. From a cosmological standpoint, HLX-1 also pushes us to redefine how we think about the architecture of the universe. If intermediate mass black holes exist outside the centers of galaxies, in satellite systems, in stripped dwarf galaxies, or in the outskirts of globular clusters, then the census of black holes in the universe may be vastly underestimated. There could be hundreds of thousands, even millions, of such objects wandering the cosmic wilderness, each one potentially carrying ancient histories and acting as gravitational anchors in small-scale structures. HLX-1 could be the first of many that finally bring these ghosts into the light. Ultimately, placing HLX-1 into the broader picture of black hole research is like finding a strange but familiar face in a crowd. It bridges categories, fills in theoretical gaps, and hints at a cosmic order that is more interconnected than we previously imagined. It is at once an individual mystery and a universal signpost, guiding us toward a fuller understanding of how black holes form, grow, and shape the cosmos across eons. As we stand on the edge of discovery, HLX-1 becomes more than just a lone example. It becomes a promise. A promise that the universe holds many more secrets like it, waiting patiently to be revealed. The future of astronomy is accelerating toward a new frontier, powered by an upcoming generation of observatories designed not just to peer deeper into space, but to open entirely new windows into reality. In this unfolding era, HLX-1 might very well be just the beginning, a cosmic messenger whispering, "There are more like me out there." Among the most highly anticipated tools in our quest to unravel the mysteries of intermediate mass black holes is the European Space Agency's Athena mission, short for Advanced Telescope for High-Energy Astrophysics. Scheduled for launch in the early 2030s, Athena is poised to become the most powerful X-ray observatory ever built. With its groundbreaking sensitivity and wide field of view, Athena will be capable of detecting faint X-ray sources that current telescopes might completely miss. What makes this significant for HLX-1 and its kin is that many IMHs candidates are faint, especially when they're not actively feeding. Their X-ray emission can be sporadic, hidden among the clutter of galactic light, or drowned out by nearby sources. Athena, with its precise imaging capabilities and high-resolution spectroscopy, could potentially resolve these signals and identify new HLX-1-like objects scattered across the universe. Athena will also be a master of time-domain astrophysics, meaning it will be able to monitor sources over time with exquisite detail. This is crucial for observing the flare cycles of objects like HLX-1. Rather than catching just a single outburst or state change, Athena could track the entire life cycle of such flares, helping astronomers map out the behavior of intermediate mass black holes with unprecedented clarity. By observing spectral changes in real time, scientists could distinguish between accretion states, determine the physical conditions near the event horizon, and even estimate the geometry of the inflowing material. That level of granularity could transform the way we identify and classify black holes that fall into the elusive intermediate category. Yet, the promise of the future doesn't end with electromagnetic telescopes. We're entering the age of gravitational wave astronomy, and with it comes an entirely new way of perceiving the cosmos. The Laser Interferometer Space Antenna, or LISA, also under development by the European Space Agency, is set to become humanity's first space-based gravitational wave detector. Where ground-based observatories like LIGO and Virgo have already revolutionized our understanding of stellar mass black holes by detecting their cataclysmic mergers, LISA is designed to detect much lower frequency waves, precisely the kind emitted by mergers involving intermediate mass black holes. This opens an exhilarating possibility. If IMHs like HLX-1 are not isolated outliers but part of a larger, hidden population, LISA might be the first instrument capable of hearing them collide. These collisions would produce gravitational echoes that ripple across space-time and are imperceptible to any conventional telescope. Through these signals, scientists could determine the masses, spins, and distances of the merging objects, gaining concrete evidence of IMBH existence and distribution in the universe. LISA will effectively function like a new kind of cosmic radar, illuminating the dark corners of the universe not with light, but with gravity itself. There's also the James Webb Space Telescope, already operational and peering into the earliest epochs of the universe. While JWST is not optimized for detecting black holes directly, it is adept at observing the environments in which black holes might form or reside. By studying young star clusters, galactic mergers, and high redshift galaxies, where supermassive black holes seem to appear mysteriously early, JWST could provide critical context for the conditions that allow IMBHs to form. It might not catch an HLX-1 itself, but it could trace the paths that lead to one. In parallel, we'll also see advancements in ground-based observatories, like the 30-meter telescope, TMT, and the extremely large telescope, ELT. These instruments will offer extraordinary spatial resolution, capable of dissecting the hearts of distant galaxies, and possibly even resolving the star clusters that might house intermediate mass black holes. They could confirm the existence of dense stellar environments like the one surrounding HLX-1, and directly measure the motions of stars that betray the gravitational pull of hidden giants. Then there are dedicated time-domain survey instruments like the Vera-C, Rubin Observatory, which will scan the entire sky every few nights, detecting transient phenomena like HLX-1's X-ray flares or optical outbursts. Its Legacy Survey of Space and Time, LSST, will likely uncover a rich trove of variable sources, many of which could be previously unseen IMBH candidates. These discoveries, in turn, could be followed up by Athena or even JWST, creating a collaborative astronomical ecosystem where multiple observatories layer their data to reveal the complete story. All of this together means that the next 2 decades could fundamentally reshape our cosmic census. We may go from knowing only a handful of plausible intermediate mass black hole candidates to identifying dozens, perhaps hundreds. HLX-1, currently the brightest and best IMBH candidate we have, may soon be joined by siblings across the sky. Some might be in quiet corners of galaxies, others drifting through intergalactic space, remnants of stripped satellite galaxies or collapsed stellar cores. Each one would help fill in the gaps of cosmic history. And in this future, HLX-1 will remain a cornerstone. It's the prototype, the proof of concept, the bright flare that led astronomers to suspect that the in-between black holes aren't just hypothetical, they're real, and perhaps more common than we ever dreamed. As telescopes like Athena and LISA come online, HLX-1 will serve as a calibration target, a test case, a familiar reference in the expanding library of intermediate mass black hole science. It will anchor our models, guide our algorithms, and inspire our theories. In a way, HLX-1 is like a lighthouse in a foggy sea, and the instruments of the future are the ships sailing toward it. Each beam of light, each gravitational whisper, each spectral signature we uncover in the years to come will bring us closer to understanding not only black holes, but the structure and fate of the universe itself. HLX-1 points to a future rich with potential, a future of discovery that's already unfolding, and growing brighter with each passing year. In the grand puzzle of black hole formation and evolution, HLX-1 emerges as a crucial, irreplaceable piece, one that helps bridge the yawning chasm between the well-understood classes of black holes, stellar mass and supermassive. For decades, astronomers have operated within a framework where the smallest black holes, formed from the collapse of massive stars, weighed in at a few dozen times the mass of the Sun, while the most massive black holes, anchoring galactic cores, tipped the scales at millions or even billions of solar masses. But this left a conspicuous and troubling void, a missing middle. Where were the black holes of intermediate mass? If black holes grow over time, evolving from small seeds into galactic giants, there had to be a transitional class. HLX-1, with its estimated 10,000 solar masses and its unique behaviors, may be the strongest evidence yet that this missing link exists. The black hole population puzzle isn't just a matter of classification, it's central to understanding the evolutionary trajectory of the universe itself. If we imagine black holes as the silent engines of cosmic evolution, regulating star formation, influencing galactic structure, and driving energetic phenomena like quasars, then figuring out how they are born, grow, and interact is like deciphering the history of the cosmos written in invisible ink. Intermediate mass black holes, by their very nature, represent the transitional evolutionary stages. They might be the remnants of the first stars, the population 3 stars from the early universe, or the products of stellar collisions and mergers in dense star clusters. Either way, they fill in the timeline between the first black holes and the monstrous ones that reside at the centers of galaxies. HLX-1 fits into this narrative with uncanny precision. Its location, far from the core of a galaxy, and its association with a possible strip dwarf galaxy or young star cluster, make it the perfect candidate for an IMBH that was once part of a smaller system and is now being absorbed by a larger galactic host. If HLX-1 really is the remnant core of a dwarf galaxy, complete with a dense stellar cluster and a central black hole, then it's a microcosm of what might have happened on much larger scales to build up the supermassive black holes we observe today. The process of galactic cannibalism, where small galaxies merge into larger ones, may not just redistribute stars and gas. It may also provide the raw material for building up black holes, brick by brick. This theory gains more weight when you consider HLX-1's behavior. Its periodic outbursts and spectral transitions strongly mimic those seen in stellar mass black holes feeding in X-ray binary systems. That's important because it suggests a continuity of physical processes across the mass scale. The mechanisms of accretion, jet formation, and radiation emission don't seem to change dramatically between a 10 solar mass black hole and a 10,000 solar mass one. This provides a rare opportunity to test theories of black hole physics in a new mass regime. If HLX-1 behaves like a scaled-up version of a stellar black hole, then we can use it to test how physical laws, like general relativity and magnetohydrodynamics, operate in more extreme gravitational environments. In this sense, HLX-1 becomes a natural laboratory for studying not just black holes themselves, but the fundamental rules of the universe. Moreover, HLX-1's very existence constrains models of black hole formation. If this is indeed an IMBH, then the conditions that led to its creation must be considered viable in simulations and theoretical frameworks. This challenges older models that suggested IMBHs were exceedingly rare or short-lived. It encourages researchers to revisit scenarios involving the direct collapse of massive gas clouds, runaway stellar collisions in dense clusters, or the hierarchical merger of smaller black holes. Each new model must now be able to account for an HLX-1-like object, one that is massive, luminous, located outside a galactic nucleus, and possibly fed by a companion star or cluster. HLX-1 isn't just a data point. It's a constraint that narrows the range of possibilities in black hole cosmology. And because HLX-1 is such a clear and relatively nearby example, it acts as a benchmark against which to measure other candidates. When astronomers discover new ultraluminous X-ray sources, ULXs, or faint off-center X-ray emitters in distant galaxies, they often compare them to HLX-1. Does the light curve match? Do the spectral shifts follow the same pattern? Is there a surrounding stellar population? HLX-1, in essence, sets the template. It's the standard candle of intermediate mass black holes, not in terms of luminosity, but in behavior, morphology, and astrophysical context. This benchmarking function also extends into future missions. As observatories like Athena, LISA, and the Rubin Observatory uncover more IMBH candidates, HLX-1 will remain an essential touchstone. Every discovery will be interpreted, at least in part, through the lens of what we already know about this singular object. Its well-documented history, relatively clean environment, and recurring flaring activity provide a kind of black hole Rosetta Stone. a reference language with which to interpret new findings. But perhaps most compelling is the symbolic role HLX-1 plays in modern astrophysics. It represents a shift in how we understand black holes, not as isolated anomalies, but as members of a vast and varied population with their own evolutionary stories. It's no longer adequate to think in binary terms, small versus large, stellar versus supermassive. HLX-1 proves that nature doesn't skip steps. There is a bridge between extremes, and we're finally beginning to map it. In the broader quest to chart the life cycle of black holes, from their chaotic births in the death throes of stars to their majestic dominance in galactic cores, HLX-1 is the first signpost along the middle path. It tells us that our models must evolve, our instruments must improve, and our imaginations must expand. For within this enigmatic object lies not just the answer to one cosmic question, but the key to unlocking many others. In the vast menagerie of cosmic phenomena, HLX-1 holds a singular place, something so rare, so perfectly poised between the extremes, that astronomers have taken to calling it what it truly seems to be, a cosmic unicorn. Once thought only to exist in theoretical models, intermediate mass black holes were the elusive phantoms of astrophysics. Too massive to be born from collapsing stars, yet too small and isolated to anchor the centers of galaxies like their supermassive counterparts. They existed as whispers in the data, tantalizing hints in simulations, and fleeting possibilities in peculiar X-ray sources. Then came HLX-1, bright and defiant, as if answering a question the universe had long been asking: do intermediate mass black holes truly exist? With its estimated mass of 10,000 suns, HLX-1 isn't merely between the known categories. It's a keystone, a bridge, and perhaps even a missing evolutionary link. Unlike stellar mass black holes, whose formation we can trace to supernovae, and unlike supermassive black holes, whose origin still stirs debate, HLX-1 stands at a crossroads. It behaves like a stellar mass black hole, exhibiting spectral state transitions, flare cycles, and accretion variability. Yet its scale speaks to something grander, something older and more significant. It acts like a mini-quazar but isn't nestled in a galactic core. It eats, sleeps, and roars like a larger predator in a smaller cage. The word unicorn, in science, carries weight. It means something so improbable, so precisely balanced, that its very existence reshapes the field. And HLX-1 has done exactly that. It has validated years of speculation about IMHs, offered a model against which other candidates are compared, and become the centerpiece in debates about black hole growth, galaxy evolution, and high-energy astrophysics. It's not just a data point, it's a pivot point. The saga of HLX-1, discovered serendipitously in 2009 by the XMM Newton Observatory, has since been followed across the electromagnetic spectrum, studied in radio silence, UV glow, optical light, and X-ray thunder. Each wavelength adds another brushstroke to its portrait. And yet, even after years of observation, it keeps surprising us. Its regular outbursts suggest a feeding cycle, likely tied to a captured companion star. Its brightness, flaring, and periodic behavior hint at an accretion process that we only partially understand. The young stellar cluster surrounding it deepens the mystery. Is this a black hole leftover from a devoured dwarf galaxy? Is it the seed of something even greater? Or is it a relic, one of the few intermediate mass black holes left behind from a primordial universe? For all the questions HLX-1 answers, it raises more in return. But this is the nature of scientific discovery, especially when something once thought mythical turns out to be real. We don't fully understand it. We haven't seen its event horizon. We can't yet prove definitively that it is an intermediate mass black hole. But all signs, all models, all comparisons lead back to one compelling conclusion: HLX-1 is the best candidate we've ever found. It's as if the universe, after decades of silence on the matter, whispered back with clarity, yes, they do exist. Here's one. And that whisper has become a clarion call. Future telescopes will hunt for more HLX-1s. Theoretical models will refine their assumptions based on its behavior. Simulations will anchor their parameters on its mass. And astrophysicists will look deeper, harder, and farther, driven by the knowledge that the cosmos still holds secrets that defy expectations, and that sometimes, just sometimes, what seems like a legend might turn out to be real. In the grand theater of the universe, HLX 1 stands as both a performance and a promise. A cosmic unicorn, luminous and rare, illuminating not just its corner of the sky, but an entire chapter of cosmic evolution once shrouded in darkness. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.